So I will kick us off. Welcome to the UKSEDI meeting, and thank you very much for all your interest. This is actually, by my calculations, the third UKSEDI meeting. Sorry, the fifth UKSEDI meeting, third that I've been involved with organising. I started this off in 2011. So I really value this meeting because in a world where we're getting increasingly worried about immediate relevance, I think we have to also hold up a banner for some pure science, and the pure science indeed has implications directly, which may even be more profound on the applications than if we just looked at applications themselves. So I'm really happy and really proud to be joined on this. We have a range of talks, as SEDI should do, covering the variety of areas of geophysics applying to the deep Earth. We have more of a sort of geomag focus in the morning and a sort of seismology focus in the afternoon, but with lots of kind of crossovers with mineral physics and with simulations and all sorts of other stuff. So a very SEDI day. So we're going to start off with an invited talk from Chris Finley, based at DTU, and there we have his title, Core Dynamics from 8 Years of Swarm Satellite Geomagnetic Observations. And for those of you who don't know what the swarm is, I'm sure Chris will be telling us very soon. Well, my calculations is we're still about 1 minute early, but I think, we got up to 42 participants. This is looking very nice. So
Richard, have you done the sort of Zoom etiquette and things like that?
No, why don't my etiquette is poor. Could you do the Zoom etiquette and say what's going on?
Yeah, so we've got a number of presentations that vary in length. We're asking participants if you wouldn't mind keeping your microphones muted just while people, so we don't have everyone talking at once. Video, I think we're going to set, Richard Bono is going to make sure the video is off just so we can save some bandwidth. The chat feature is going to be disabled, so if you'd like to ask a question, please put it in the question and answer, and then Richard Holm will probably read them out at the end, and Richard Bono and I will hopefully try and make sure your questions get passed on to Richard. So please just use the Q&A, which should be in the center of your screen at the bottom. And the presentations are being recorded. So if you don't want yourself being recorded, then don't do anything that would cause you to be recorded. And that's all. Thanks.
Okay, thank you for that, Chris. Oh yes, the poster session. Richard, no, he's run off. There he is. Good.
I'm here. Yeah, so there'll be a poster session to the lunch hour. This is the link. I'll make the link available again once we're a lot closer to it, and we invite all the poster presenters to very briefly, 30 seconds, just say hi and maybe the title of your poster in this Zoom session so that people can start linking names and faces and work together, and I hope to see everyone there. It uses the GatherTown app, which maybe you've seen before, and if not, it's pretty straightforward to figure out, and that's my piece.
Okay, so I think that brings us on to Chris, and also has the advantage I'm going to mute myself, so I will shut up. So Chris, take it away.
Okay, can I share screen here? Is someone else sharing at the moment? Yes, great. Okay. Can you see my screen and hear me okay? Does it look fine?
Looks good.
Excellent. Thank you. So good morning, everyone. It's a pleasure to be here talking to UKSEDI and at the RAS. So thank you very much for the invitation. So this morning, I'm going to give you an overview of some of the exciting things we've been learning concerning core dynamics from 8 years of satellite observations from the SWARM mission. And this is very much going to be a personal perspective, but I'd like to thank the people listed here who I've collaborated on with various of these topics that I'll be telling you about, and also who have kindly allowed me to show some things even ahead of publication. So just to kick things off, some motivation. So this is a meeting that's all about study of the deep earth. And as we all know, studying the deep earth is not easy. And in particular, it's difficult to get solid observational evidence to test our ideas. So regarding the Earth's core in particular, the main source of information we have about the motions of the core is the Earth's magnetic field and our observations of how it's changing in time. And in particular, if we look at the so-called magnetic induction equation, we see that the rate of change of the magnetic field B, which we call the secular variation, is given by the velocity in the core, U, acting on the magnetic field. And then we also have some ohmic diffusion as the magnetic field is decaying because of the finite conductivity in the core. So the point here is that by looking at observations of the time changes of the Earth's magnetic field, we can get information on what's happening within the core. And if we see time changes of the secular variation, we can get information on the time changes of the motions of the core, that is the core dynamics. So what we're trying to do, and what I'll be concerned with here, is how do we use detailed knowledge of Earth's magnetic field and its time variations to probe the motions of the liquid metal in the outer core, which are shown schematically by this picture down in the bottom right. So I'm going to, in particular, focus on what we've learned from satellite observations, and in particular from the SWARM mission over the past 8 years. And I'll talk about, in particular, what we're learning about sub-decadal core dynamics and possible future applications for how we can use these type of methods for probing the properties of the deep earth. So I've already mentioned the SWARM satellite several times. So for those of you who don't know, SWARM is a constellation of 3 identical satellites designed to carry out the best ever survey of the Earth's magnetic field. They were launched in 2013 together into an orbit a little bit above 500 kilometers altitude. And then 2 of the satellites were pushed downwards, Alpha and Charlie, and these have now descended down to about 436 kilometers altitude. And then there's a 3rd satellite, SWARM Bravo, which was pushed upwards, and it's by now descended to a little bit below 510 kilometers. And the point here is that we have different orbital planes for the lower pair and the higher satellite, and that gives us coverage of different local times. And that's very important for separating especially ionospheric magnetic signals from what we're interested in, which is the signal from the Earth's core. So the altitude of the satellites is currently decaying slowly, but we are in good shape. The instruments on board the satellites are functioning well, and we have a lot of fuel still on board. So what's happening at the moment is we're just entering, the new solar cycle is beginning to pick up again. We've gone from solar minimum and the solar cycle is picking up. So the plan now soon is to push at least the lower satellites upwards to stop them from being pulled down by the increased drag that happens when the solar activity is enhanced. So with this in mind, we're really planning scientifically for a very long SWARM mission. So we now have 8 years of continuous satellite observations of the magnetic field. So what's shown in this next slide is an example of what SWARM data looks like. So on the left here is 1 day of SWARM data. So the lines here are showing the direction of the magnetic field, and the color is showing the strength of the field. So orange is where the field is stronger at higher latitudes. And this is just from 1 day of SWARM data. So you see already there's decent global coverage. And what this means is that then when we look at time scales of the magnetic field that are relevant for the core, so that's time scales maybe of a year and longer, then we have really excellent global coverage, even if we are doing a lot of selection of the data to try and discard times of disturbance due to solar-driven disturbances. And what's shown in the right here then is a selected data coverage that we would use to study the core field. So blue here is regions where we only use the information on the field intensity at high latitudes. And the reason for that is because we get some electrical currents flowing down the field lines at high latitudes. These are auroral current systems that disturb the field that we're interested due to the core. So we only use intensity data at high latitudes, and we use the 3 components of the vector field at mid and low latitudes. So what you can take away from this is that we have very good global coverage on a timescale of a year. So what then do we do with all these observations to study what's happening in the core? So in order to do that, we first construct models of the geomagnetic field. So the first step is that we write the magnetic field V as the gradient of a scalar potential. And then, at least for the internal part, we're expanding that in terms of a basis of spherical harmonics. So PNM is the associated Legendre function. And then we have GMN and HMN, where N is degree and M is the order of the spherical harmonic. And these are telling us about how much of these different spherical harmonic patterns we have making up the potential. And then, of course, what's interesting to us here is that the magnetic field is changing in time. So then we expand these spherical harmonic coefficients in a basis of 6th order B splines in our case. And we use 6th order splines because we're going to want to look at several time derivatives of the field. In addition, we co-estimate an external magnetospheric field, and we determine simultaneously with the internal field some parameters about the spacecraft alignment. This is based on the work of Niels Olsen in 2006, and that's how we produce a field model that is called the chaos field model that's produced by DTU on a regular basis every 3 or 4 months from the swarm data. So in practice, how do we determine the coefficients of the field model from the data? Well, it's a regularized nonlinear least squares problem where we have the satellite data D, and F of M is a prediction of the model for the observed data. And then we have weights for different field components and different types of satellite data. And then in addition to minimizing the fit to the data, we minimize some measures of the complexity, especially related to the time variations of the field. We try to solve for things that are fairly smoothly varying in time when we build these field models. So for the results I'm going to show, I'm using swarm data, vector data, and scalar data at high latitudes, and also differences between the swarm data moving either along the track, which gives us extra information about north-south variations in the field, or also across the track, because we have a pair of satellites flying side by side. We can also use east-west gradients. And in this chaos model, we also use data from earlier satellite missions, CHAMP, Ørsted, and SAC-C, and we use ground magnetic observatory data as well in the form of revised monthly means. So we have, in total, the model I'm going to show you uses a bit more than 4 million data. And this is the latest release of the chaos model, chaos 7.8. And you can get the coefficients of this model from the web page shown below. And we also have a Python package that was produced by Clemens Kloss, postdoc at DTU, that allows you to conveniently work with this chaos model. And just to give you some idea how well this model fits the data, so it fits it to less than 2 nanoteslas regarding the scalar field data at non-polar regions. And when we look at differences along the track, we're able to fit down to about 0.14 nanotesla on RMS, and cross-track differences to about 1/3 of a nanotesla. So we're really able to explain a lot of the detail that's in the data with this model. Okay, so now let's look at what the magnetic field we see from this swarm data looks like. So this is a first picture of the radial component of the magnetic field at the Earth's surface, where orange is the field line coming out of the core, blue coming back in, and the strength of the field of the radial component is indicated by the depth of the color. So it's rather featureless at the Earth's surface, mostly dominated by the dipole, but you see there are these high latitude concentrations. If we then evaluate the model down at the outer edge of the core, so assuming that there are only weak sources between where we measure and the core mantle boundary, then we're able to get images of the radial field at the core surface. So many of you will be familiar with these maps. So this type of image of the magnetic field at the boundary of the core was first obtained really with data from the MagSat satellite back in 1980. And the basic structure of the field has not changed radically since then. We have concentrations at high latitudes, and we have a series of intense field patches at low latitudes, and we observe them in particular moving westwards. So what's new really with the recent satellite data is not so much looking at the morphology of the field itself at the core surface, but rather at the time derivative of the field. So this is this secular variation I mentioned at the start. So this is the first time derivative of the radial magnetic field plotted at the core surface. So what you see here is that most of the change in the magnetic field is happening in the hemisphere centered on the Greenwich meridian, and it's happening most intensively at rather low latitudes, below 30 degrees. There's less happening in general at mid latitudes, and at high latitudes, there's not much happening in the southern hemisphere. In the northern hemisphere, there's a distinctive feature, and I'll come back to that later. So this is the pattern we have for the secular variation at the outer edge of the core in 2014. And if I move forward here, this is what we have in 2021. So if I flick back between these, you can see how much this pattern of the time changes in the Earth's magnetic field has changed during the time when we have data from SWARM. So the change is minor, but it certainly is changing. And so it's these time changes of the secular variation that are going to give us information on how the core flow is changing. So a few interesting features here. So if you look at this thing under Indonesia, there wasn't much there in 2014. There certainly is a signature under Indonesia in 2021. Okay, so, and I'll go on in the next page to switch the center of the map. Now it's centered on the Pacific rather than the Atlantic. So generally the Pacific, historically speaking, has been thought to be rather quiet, but interestingly in the past decade when we have the SWARM data, there's been a number of interesting changes happening in the Pacific region, and I'll focus on that a little bit later in the talk. Okay, so this is the essential data that we're using as input to determine the patterns of the core flow. So I'm now going to show some images of the patterns of the core flow that we obtain if we take this secular variation data and we invert it for the core flow. So what's shown here, this is a flow inversion carried out by Nicolas Gillet based on the Chaos 7 model, which I've just presented. So what's shown here in blue colors are where the flow is westward. Orange color is where the flow is eastward. And these black dots here are tracers of the core flow. So what you see is that most of the core flow, so this is at the surface of the outer core, is westward. So especially, so here, this is Africa, and this is America. So the flow is westward, going from Africa over the underneath the Atlantic over to the Americas, and then it then moves northwards and southwards, concentrating especially here under the Bering Strait into a very intense region of westward flow. Then it comes back down again over Asia in a meridional leg, and then is going westward again. So something interesting here is that it's not completely featureless in the Pacific, although the majority of the flow is sort of moving around the edge of the Pacific. So the next picture here is showing the same image, but in 2020. So this is now how we're seeing that the pattern of flow is changing over the time period of the SWARM data. And certainly at low latitudes in the Pacific region, we're seeing some changes over this period. This eastward flow over these 8 years has certainly intensified. But the general pattern of the core flow with westward flow strongest under the Atlantic hemisphere is essentially unchanged. So I should just mention that in order to carry out these core flow inversions, it's a difficult inverse problem. You can't determine this from the observations alone. You also need some prior information. So these particular models from Nicolas Gillet, they are using as prior information some statistics obtained from geodynamo simulations from Aubert and Gillet paper from this year. And Nicolas' method of core flow inversion is also rather sophisticated. It takes into account the error, because we don't know the entire observed, or we don't know the entire pattern of the secular variation. Our observations are limited to large length scales. And it also accounts for the error due to the fact that we're not able to properly determine the magnetic diffusion. The impact of magnetic diffusion is not fully accounted for in this situation. It's treated as an error. Okay, so this is the basic pattern of the core flow we're getting from the swarm data. I'll just show a second example. This is from a different study by Kathy Whaler, where she's processed the swarm data in a different way and is using a simpler choice of regularization. So this particular map is with a strong, so-called strong norm, where small scales of the core flow are strongly suppressed. And the basic pattern is the same. The flow is westward here from Africa over the Atlantic. Then it's going in the meridional direction. And then we have a strong westward flow here under the Bering Strait. Then it's going equatorward again. So it's this general pattern, which we sometimes refer to as a planetary scale gyre. And this is obtained regardless of the way we process the satellite data, and different assumptions can be made regarding the prior information. And this pattern is essentially the same. And I noticed that Kathy also has a strong eastward flow here under the Pacific hemisphere. And I think an important result that occurs both in Nicolas' work and also in Kathy's work is that although the details of the core flow pattern can depend on the choice of regularization, its time changes are really quite well constrained by the data. So time changes in these patterns are rather robust. So something that I've already mentioned is that there's a very distinctive pattern of secular variation at high northern latitudes, where you have positive, negative, positive pattern sitting on around so the red circle here is the imprint of the tangent cylinder around the inner core onto the core surface. So we have a very distinctive pattern of secular variation at high northern latitudes. And Phil Livermore has showed how you can explain the essential details of this pattern just by having a very strong westward flow sitting here right on the tangent cylinder. So this is a strong jet of core flow at high latitudes. And so this nice conceptual model from Phil explains very well this signal we see at high northern latitudes. And when we look at more general core flow inversions, such as the work of Nicolas Gillet, we see that this jet at high latitudes is in fact part of this large-scale circulation, where we have westward flow under the Atlantic hemisphere, then coming up to high latitudes, intensifying here and producing this signal in the secular variation. So you see now, looking from this angle, we see a very clear asymmetry between the Pacific hemisphere and the Atlantic hemisphere, and we have this planetary scale asymmetric gyre. So, of course, an obvious question is then, well, what in terms of core dynamics can be responsible for this asymmetry? It certainly begs the question. So there's been a number of proposals. This perhaps could be an imprint of inhomogeneous heat flux at the core-mantle boundary. That would be, I think, a natural way to explain this kind of asymmetry if it was there on the very long term. Julien Aubert has also shown that if you have more buoyancy happening at the inner core boundary in the eastern hemisphere, that very nicely generates this gyre structure and can explain all the essential details. Another possibility is that we're just looking at one snapshot of a very turbulent outer core convection, where it happens to have this kind of large scale asymmetry. So This question is, I think, still open as to the real origin of these things, but the longer we have good observations of this gyre structure and how stable it is, the better we'll be able to distinguish between these different hypotheses. Okay, so that was the basic pattern of the core flow. I want to now move on to time changes of the core flow. So this is now a movie showing not the first time derivative of the magnetic field, but the second time derivative. So that's what we call the acceleration. And this is a movie at the Earth's surface over the past 20 years. So I'll just play that again. So what you see now when we look at the second time derivative of the field, and we have such good data from satellites over the past couple of decades that we can do that, the acceleration is much more dynamic. And especially here in the last 8 years when we had swarm data, there's some high amplitude accelerations have been happening in the Pacific region. So if I just play the last 8 years again, you'll see that there's accelerations in one direction and then going in the opposite direction and then changing sign again. So there's really something to be explained here in terms of the accelerations of the magnetic field in the Pacific region in the last decade. And one can also try to track this acceleration down to the core surface. So as you go down to the core surface, of course, you see more small scale details. And looking in the past 10 years, you'll see that there are coherent structures that appear in the secular variation under the Pacific region, even when we track it down to the core-mantle boundary. So that's the entire secular acceleration pattern. So because a lot of the action is happening here at low latitudes, one thing you can do to try and get an overview of these time variations is to plot things in terms of time longitude plots. So here, what I've done is I've taken this acceleration along the equator, and then I'm plotting that for all longitudes, and then as we move forward in time. And this is now over the past 20 years using data also from the earlier satellite missions. And here is the results of this acceleration for two different ways of looking at the data. So on the right is the results from the swarm, from the chaos magnetic field model. So this is by construction, because of the way we regularize it in time, it is rather smooth. On the left here is an alternative approach where we try to do a localized inversion for a certain time window at a certain location at the core-mantle boundary. And the basic pattern that we get from these two approaches, again, agrees fairly well. The localized approach has got no assumption of smoothness in time, so it's a bit rougher. And so you maybe see some more details, especially when we get the good swarm data coming in later here. But it's also a little bit noisier, especially before we had swarm, we only had satellite data from platform magnetometers, so not dedicated high performance magnetometers. So here we use data from that was collected from the Cryosat mission, which wasn't really designed to study the Earth's magnetic field. So it's a bit noisier in this region. But one thing to take away here is that if you look at a particular longitude, what you'll see is at a fixed longitude, the sign changes of the acceleration. So it goes blue, orange, blue, orange. So we're getting these oscillations at fixed locations. And there's also perhaps indications that these acceleration patterns are moving either eastwards or westwards. Now, if you get a change in the sign of the acceleration from negative to positive, so the acceleration is like the trend in the secular variation. So if the acceleration changes sign, you tend to get a V shape in the secular variation, and that's something called the geomagnetic jerk. So when you get a sign change here in the acceleration, that's the source of one of these geomagnetic jerk events. Regarding the propagation, I think one has to be a little bit careful because we're looking here at something that's band limited. So we can't see all length scales of the signal, and we're also limited in the time series length, and also we can only go down to time scales of maybe 1 year minimum. So it's tempting to think about these in terms of propagation, but we need to bear in mind that we're looking at a band limited signal here. Okay, so the question is then what's responsible for these time changes in the secular acceleration? Well, if we then look at core flow inversions, so now I'm back looking at the core flow inversions, and if one filters the core flow to just look at subdecadal timescales, what you see is that there are oscillations in the east-west or azimuthal component of the flow, especially. So what's shown here is at one particular longitude in the Pacific as a function of of latitude and time. So under the Pacific at a certain longitude, we get oscillations in the azimuthal flow that are very concentrated at low latitudes. So here, this is a time varying oscillation that we see especially clearly when we have the swarm data over the past 8 years. And below, it's also as a function of time of this azimuthal flow velocity, but now as a function of longitude. So here you see that this is longitude 180 under the Pacific. So that's where we see this oscillating azimuthal flow feature. That's what produced the acceleration changes that we saw in the observations. So there's distinctive, the thing to take away here is that we have non-axis symmetric azimuthal flow east-west fluctuations at low latitudes. And this is work by Nicolas Gillet that he kindly has allowed me to show in advance of publication. And this type of signature is seen by several groups. So Kathy Whaler has also looked at time changes of the core flow. She has looked at flow accelerations under the Pacific. So now this is at different longitudes as a function of latitude and time. And now this is the acceleration of the azimuthal flow. And Kathy sees, especially around 2017, a change of the azimuthal flow acceleration from being negative to positive. It's not so clear at different longitude in the Pacific. And then if we go further over, we do see again this signal, but it's got a different sign. But it's especially clear in this region. And we think that this change in the azimuthal flow acceleration seems to explain this time change in the field acceleration, which is giving this geomagnetic jerk event in the Pacific region in 2017. So again, what I'm trying to show here is that several different groups are seeing similar patterns regarding this subdecadal azimuthal flow fluctuations at low latitudes in the Pacific. So again, then once we see something in the observations and in the core flow inversions, the question is, well, what core processes, what's this telling us about what's going on in the core? And we're very fortunate because the technology regarding simulations of the magnetohydrodynamics in the outer core has really been developing over the past decade. And people are understanding better how to scale these simulations towards the Earth's core conditions. And so in my opinion, some very exciting work has been done by Julien Aubert in this regard. And he has seen features in his simulations that have patterns of the acceleration. So this is a map of the field acceleration from one of his simulations at the core-mantle boundary. And it shows time-changing acceleration pulses that look very similar to the observations in their amplitude, in the fact that we get alternating signs of this acceleration, and in terms of their geographical location being at low latitudes. And so we can also study these things, of course, in time longitude plots. And we see a number of these events. So running the simulations for many, many turnover times, we can get a whole catalog of such geomagnetic jerks and acceleration pulses, and we can study what underlies it in terms of the core dynamics. And so this is something that's been studied in terms of a consortium funded by ESA, the 4D Earth Core project. And they're looking into this catalog of jerk events and dynamo simulations and trying to connect these with the observations. So, of course, the advantage in the simulation is you can look within it to see what's causing these things. So this is a kind of a busy plot, but it's showing here density anomalies in black and magnetic field in blue and orange. And what happens is that you get a density fluctuation of plume, and then the signal from this propagates outwards, and it's seen especially in the azimuthal flow acceleration, which is what's seen in blue and red here. And this is rather quasi-geostrophic, so columnar within the core. It propagates outwards, and when it reaches the core surface, we get oscillations in the azimuthal flow direction, very similar to what is seen in the core flow inversion. So the arrival of these hydromagnetic waves at the core surface is capable of explaining many of the features that we see in the observations. But I should say that there are other possibilities. So especially Bruce Buffett and his colleagues have explored other types of waves that rely on there having a stratified region close to the outer core boundary. And they are exploring whether these can also explain these rapid features. So this is a topic that's still being discussed and in development. And one last thing I'd like to mention is that whenever these waves arrive at the core mantle boundary, if there's a conducting lower mantle, there will be a torque on the mantle from these waves arriving at the core mantle boundary. So what's shown here is from different events, spikes in the torque that occur near to the times when we have these pulses of acceleration close to the core mantle boundary. And then if we look at the change of the length of day of the mantle, this torque pulses translate into inflection points in the simulations in the length of day, rather similar to things Richard has shown looking at in the observations of the length of day. So the interesting thing is that in the simulations, these signatures depend on the properties of the lower mantle and, for example, whether the outer core is stably stratified. So by studying these wave events, it's likely that we can learn about the properties of the lowermost mantle and the upper core, which is a region we would definitely like to study in detail. So I'm just finishing up here. So let me summarize. So I think I've shown you that we have now 8 years of high quality data from the swarm satellites, and these are really, it's the only way I know where we can get rather direct information about what's happening regarding the core dynamics on a global level. And what we really need now is 8 years is not really long enough. We need longer time series with this global coverage. So as long a swarm mission as possible is really crucial for further advances. In terms of the core flow, this seems to be dominated by this planetary scale gyre westwards under the Atlantic hemisphere and with this jet under the Bering Strait. And the new thing is that we're seeing these azimuthal flow changes at low latitudes under the Pacific. And geodynamo simulations are providing a possible way of interpreting these in terms of hydromagnetic waves. And the study of these, I think it's exciting for the future to try and use these to learn more about the state of the core interior and core mantle boundary properties. So I'll finish there. Thank you.
Thank you, Chris. So in the Q&A, we actually have a question. So I'll just keep going and ask the question. So this is from Andy Biggin. Fascinating talk. What do you think your favored core flow models imply for global or, whoops, it's gone away.
Oh, my fault. Switch to the answer tab, Richard.
Okay, to the answer tab, here you go. What do you think your favored core flow models imply for global or regional stratification of the uppermost core? Could the prior be suppressing it?
Yeah, so certainly for the core flow inversions from Nicolas Gillet that I showed, these are based on priors from a geodynamo simulation, which doesn't have stratification. That is for sure true. So I think regional stratification, such as I think John will talk about later, this is I guess a possible explanation for why typically we see something like the Pacific as being rather quiet, but then then you have to find a way to explain these rapid acceleration pulses we're currently seeing in the Pacific. So now perhaps there's ways to do this in terms of waves in the stratified layer, but I think this is still work in progress. So from my point of view, looking at the best flow models we have and the dynamo simulations, I'm quite, I find it rather compelling how well we can explain lots of the details of these acceleration pulses without needing stratification. So from my point of view, from these observations, it's not a requirement that we have stratification. That doesn't mean it's not there and there's not ways that you can explain these things if there is a stratified layer, but models without stratification can explain all the details that I've just presented.
Okay, I'm going to use presenter's privilege and grab a quick question. So you said several times that the swarm is going for a very long term. Now that's remarkably lacking units. Whenever you put any data in, I always demand units on things.
Yeah.
So what are you, I mean, obviously we would like permanent.
Yes.
But do you have any feelings on the practicalities and how long we're likely to get?
Yeah, so I guess there's two issues here. One is what's from an engineering point of view possible. And I think there it looks very promising especially with Swarm Bravo, which is the higher satellite. It has a lot of fuel and it's decaying very slowly. And there's no evidence for any degradation on the magnetometers at that stage. So we're certainly planning to, at the moment, for the Swarm satellites to come down during the next solar minimum, right? So that would be around 2030, okay? Now, then of course, it's a question of funding. So if ESA continues to be supportive and excited about the type of information we're getting from the Swarm satellites, and it's certainly, when you have such fantastic infrastructure there and operating, it's a lot cheaper than launching something new. So we're very optimistic that it will be continued to be funded. But the way ESA funding works is that it's funded at, say, 3-year blocks at a time. So at the moment, we're just about to go through the process of the next extension, which we're extremely positive about. But you can't say definitively because it's a question of funding, of course. But in terms of engineering, and if we can continue to do good science with the data and show that it's useful, then I think we have a very strong case for Swarm going out at least to 2030, I hope.
That's really good news. Now, there are, in fact, 2 extra questions in the Q&A, but we've run up against 11:15. And particularly given the poor next speaker, I'm anxious to move on for this point. So, Chris, if you could have a look at the Q&A, and then you can see the questions to answer directly. So the reason I'd like to go on to the next speaker is because it's about 3 in the morning for him. So Yufan Zhu is joining us from West Coast of the United States, and this is certainly deep earth science above and beyond the call of duty. He's going to talk about thermoelectric liquid metal magneto convection. So, Richard, have you got it switched on? Yeah, it looks like Yufan. Do you want to say something?
Yeah. Can you guys hear me?
Yes.
Okay. Okay. Let me share my screen first. Okay, sorry, one sec.
I can see that. Lovely.
Great.
I can see.
Awesome. Can you see my screen right now?
Yep.
Okay, cool. First of all, thank you very much. It's a pleasure for me to be here. Although it's kind of early in the morning, but I'm still super pumped. You know, I love this group of people, and yeah, it's really my honor to be here. So I think Dr. Finley just gave a fantastic talk, and actually connects very well to my project and to my presentation today. So what I'll be talking about is the thermoelectric liquid metal magneto convection. And this is a laboratory study, actually. We're basically trying to provide some of the new perspective into interpreting some of the core surface radial fields data and time variant, interesting mechanisms that could happening at the level of the CMB. So this is still although we just published this paper on GFM, but it's still, for me, is a project in progress, right? So we're still trying to do something interesting with this concept. First of all, let me introduce my co-authors here. They are Dr. Susanna Horn from Coventry University from UK, and my advisor, Jonathan Arno. We're from University of California, Los Angeles, and I'm a PhD student. Okay, so first of all, before I go into the thermoelectricity Magneto convections, let me just briefly recall some of the concept of the thermoelectricity. So for this this presentation, I think the most important thing is the Seebeck effect along with Thomson and Peltzer effects from the electric effects, that the temperature gradient could generate a electric potential in a certain material or two different materials. In the mathematical formulation is this phi TE, which is the electric potential scale with a Seebeck coefficient times the temperature difference along the material. For example, here is a very cool schematic that you can see there's different distribution of the electrons, right, in this metal bar, where because one end is hot, the other one's cold, and you have a temperature gradient, and that gradient it's basically what generates this voltage across these different ends. Of course, different material have different response to this. And some of them actually has the reversed voltage, from cold to hot. And if we combine the two materials properly, and if we have like a very different Seebeck coefficient, for example, at two junctions along these two different medium, you would imagine to form a current loop, right? And then the current would go different directions and basically across these two junctions. Okay, so when you have and this can be a very interesting mechanism because back in early 1979, Shircliffe's actually mentioned in one of the paper that the thermoelectric currents can generate from the temperature gradient with the perpendicular B fields can exert Lorentz force on the liquid metal. And actually there are applications like crystal growth and the steering metals. So these currents are actually sometimes can be significant enough to affect the dynamics of the liquid metals. And in our field, it's we're talking about the core fluids, and it might have some relevance to it. And in all these previous setup of the thermoelectric MHD per se, the temperature gradients are usually imposed. So that's actually inside of one of our motivations that in the convection system, right? So we would see the temperature gradients to be generated everywhere, across the layer or even in horizontal distance. So I will elaborate on that in the following slides. But let's also take a look at the thermoelectricity and the core convection itself. So actually, the thermoelectricity has been proposed to occur in other planetary cores, such as Mercury, like Stevenson 1987, and the following paper just 2002. And basically, what it says is along the mantle and core, they are trying to explain why the Mercury has so large magnetic field that they cannot explain from the maybe the seismology or the other models. So they propose that there might be a thermoelectric dynamo model, inside of the Mercury, and that can generate the current loop can generate a toroidal B field. and that reinforce the toroidal field that you can measure. But this is still like kind of alternative explanations for that, and it's focusing more on the field generation not intended for the Earth core-mantle boundaries. But as we're looking more into this, the TE effects on the convection system, such as core flows and core-mantle dynamics, actually remains unknown and very little studied. So that's why we're saying like the turbulent liquid metal convection system can generate significant temperature gradient itself. So we don't need to impose another temperature gradient in order to let the thermoelectricity happening in the system. So let's take an example of the current day core-mantle boundary. And this is a schematic adapted from some of the current latest studies that along the Cmb, where you have this topography, you have a very large scale stable thermochemical piles that might relate to the large LLSVPs, right? Large low shear velocity provinces. And also on the edge, sometimes you have a smaller scale ULVZ, ultra low velocity zones, and those are density anomalies and could affected the topography of the Cmb and also introduce the temperature difference. For example, for here, if we have a down going slab, which presumably would have a lower temperature than what's inside the stable thermochemical piles. Of course, the different temperature, the temperature gradient can also be induced by other things like regional stable stratified lenses or topographic variations and exactors. They can also induce these temperature gradients along the Cmb. So since there's a temperature difference, and if we think the thermoelectricity matters at the Cmb because we don't know the physical property yet, there might forms current loop, right? So the JTE and also together with the magnetic field, there could be very interesting Lorentz force, and there'll be torques working on the core fluids. And we're going to build experiments and to test that idea and see how that work in the reality. So this is our experimental setup. So basically, we're building a classical turbulent, really Barnard convection, and with the vertical B field. So the B field will be imposed on top of this tank over here, which is heated at the bottom and cooled at the top. And our working fluid is liquid gallium, which have very low Prandtl number. That means the viscosity is very low, and it can flow very fast in this tank. Where normally you would see a large-scale circulation start to set up when you become sort of turbulence, and it can self-sustaining the temperature gradients at the top and the bottom. So the hot plumes here will inevitably heating a little bit more than the other end of the LSC, where this cold plumes were induced a little bit lower temperature at these two boundaries. So as the comparison and the control group, so we set two suites of the experiments with different boundaries. First one is insulated, electrically insulated with the Teflon coated aluminum at the top and bottom. And the second one is electrically conducting, which is copper, right, for top and bottom. And we also have temperature sensors on top, mid plane, and bottom layer, and there are 6 on each layers and arranged azimuthally aligned in the vertical direction. So the thermal signal can be used to detect the fluid motions in the liquid metal because as I said, the Prandtl number is very low. And also liquid metal can conduct heat pretty fast. So you can really see a heat signal moving across the tank if there's a blob of the plume that moves. So we're using this to study basically what's going on inside the tank, and with the different boundaries, of course. Here is a close-up look to our apparatus. As you can see, there's a heat exchanger on top, and we have a heat pad over here. And basically, we can change the tank height to reach different parameter space, and we're constantly cooling and heating it. And so we're also applying a uniform magnetic field on top. Okay. So let's talk about what have we found. First of all, if the electrically insulated boundaries are, we first look at the electrically insulated boundaries. Here I show a mid-plane sidewall temperature contour, and on the x-axis is the azimuth angle, and which correlates to the thermistors, right, on the left side, and these are the midplane. So you can see the global structures here. And on the y-axis is the thermal diffusion time, and one thermal diffusion time in liquid gallium, it's about, in our tank, it's about like 13 minutes. And if you do numerical simulation, you would know like one thermal diffusion time will be 100 of the free fall time, which is a lot to simulate if you're running running numericals. So that's one of the advantages of doing experiments, laboratory experiments, that you can have such long time scales. And let's look at the temperature, and the different color represents the different temperature in Celsius. So here we set the really number, which is the buoyancy over diffusion, to be about 1.6 times 10 to the 6, and there's no magnetic field, right? So just really Banach convection. And as you can see, when there's no magnetic field, there are two hot plumes from one side and the cold plumes from the other side. Correlates well with the plots of the schematic over here. And when you apply negative downwards magnetic field, you start to see the flow lines up pretty well. It's become more organized because the magnetic fields try to dampen the motions perpendicular to the field, right? This same thing goes to the plus when you flip to B field. So nothing changed, and the LSC is persisting. It persists in the Magneto convection, and is agree with our expectations with the standard low RM approximation, where the magnetic field simply dampens the horizontal motion, right? Oh, and MC's characteristic frequency agrees with the predictions, where you see this small oscillations. It actually agrees with the previous predictions, the frequency predictions. Now let's look at the electric conducting case, right? Let's take it slow. So we can still start from the middle, where there's no magnetic field imposed. By the way, this time is consecutive. It's basically continuous experiments. So we run it, and at some point we just switched off the magnetic field, and the other point we just turn on, but in the reversed direction. So in the middle, it's very similar to the previous case, and we have a Rayleigh number about 1.8 times 10 to the 6, about the same. And when you apply a B field, and you start to see that the structures start to process in the prograde directions. Still, this bimodal structures, right? One part is at the one time you can see half of it is blue, the other half is red. So it's prograding, it's processing the prograde directions. And when you flip the B field, it actually goes the other way. So that's very interesting. And it seems to, we seem to find a slow traveling magneto precession wave mode. And it's sensitive to the polarity of the magnetic field. And it only exists with the electrically conducting boundaries. So that's very weird and interesting. And we think this is what we call a thermoelectric magneto convection flow. And then we go on build an analytical model for it. So bear with me. And when we have LSC, it creates horizontal temperature gradients at the top and bottom boundaries, right? And this temperature gradient will give rise to the thermoelectric currents across two different metals. And these different metal loops, with the vertical B field, it would generate Lorentz force, which in this case J cross B, and it will be in and out the paper. And the net, basically the net, our idea is the net Lorentz force would generate torques that are perpendicular to the moment of inertia of this whole LSC, large scale circulations. And that's why it persists. Okay, so in this three-dimensional way, this is probably a clear pictures where you see, first of all, you have this angular velocity over here, and basically the forcings, the Lorentz force on the top and bottom would generate a torque and that torque is perpendicular to LSC, just like a spinning top, right? If we assume this to be a solid disk, which in the zeroth order, that's where we start from building this analytical model, and use Euler's equations and plug in the very ugly looking thermoelectric net torque, which you can calculate from the thermoelectric potential if you do the math properly, and especially using the copper and gallium system. And we just use this term is to be tau. And combine these two, you can solve for basically the precession angular frequency. And to be interesting, this frequency is scaled with linearly dependent on the magnetic field, right? So that means if we flip the B field, this precession also flip its directions. So that's very important. So how does that model compare to our experiments, right? So
Okay,
let's look at
a minute or two finishing up, okay?
Okay, got it. Thank you. So we fixed the Rayleigh number and we vary in the basically different B fields, magnetic fields. And we see that our data, which is the black circles, are fairly close to our best experimental models, the analytical models, within 16%. And for such a zeroth order model, it works amazingly well, I would say. And the Lorentz force becomes comparable with the inertia. That's when the LSC breaks down and our precession modes just disappear. Let's come back to this picture. So we have a current loop might be generating at the Cmb with the magnetic field that would generate the torque and Lorentz force in and out of the paper right now. And that could be very interesting and can be changed when the B field is flipped. When it's alternating or when it's the reverse reversal, you would see some reversed, basically a symmetry breaker, right? Okay, so we define the Seebeck number to quantify like basically how important this thermoelectric TEMC phenomenon would happen. It's a ratio between the TE potentials and motion-induced electric potentials by liquid metals. And if we just taking some of the quantities for basically the Cmb, we would get something like this in this plot, right? So these black cases are the ones in the experiments. The red lines are ULBZs, and the orange ones are basically thermochemical piles. So we found the flows are usually at 0.1 for the Seebeck numbers, and in order to work in the thermoelectric piles or ULBZ, we would imagine the thermoelectric property at the Cmb would be about 10 to the 2 and 10 to the 3. So it's quite high. And this property is currently unknown and possibly can be studied by first principle simulations. Frankly, many semiconductors already have this number, like silicon could have like 800 moles per Kelvin. So it's very interesting to see in the future, maybe we can get more information out of it, and maybe this can be a very interesting mechanism. So Seebeck coefficient can change with pressure and temperature. That could make it more possible or less possible. So in summary, if you didn't learn anything from this talk, but I hope this is the takeaway point that we experimentally investigate the thermoelectric effects and in this liquid metal magneto convection system, and we observe this precession mode, and it could relate it to the thermoelectric effect between the liquid metal and the conducting boundary. And the currents with the B field can exert torques on the core fluids near Cmb. This could be a potential new dynamic mechanism to explain some of the core-mantle coupling and dynamics, and maybe explaining some of the field reversal. And it provides the natural symmetry breaker between normal and reversed geomagnetic field orientations. And we need further study. So thank you very much for listening, and also thank for NSF for supporting our research. This is our latest publications. It's a QR code. If you can scan it, it will lead you to the link. Thank you very much.
Thank you very much, Sufan. Now, unfortunately, we've run over time, but what I've seen happening actually is in the Q&A, there've been a couple of questions that came for Chris that he answered in parallel with listening to you. So if anybody has any particular questions they want to raise with you, then we're still in possible, you can still feed them into the Q&A. And in fact, I've got some questions for you, but maybe we can talk about it at lunchtime. So we're going to have to move on to the next talk. So that'll be Yael Engbers. And I won't give a title because I'm sure she will.
Hi, I will just share my screen. Can people see my screen?
Looks good.
Okay. Well, good morning, everybody. My name is Yael Engbers. I'm a PhD candidate at the PaleoMag Lab at the University of Liverpool. And in this talk, I would like to present part of my PhD thesis, where we created the first non-zonal time average field model for the Miocene called M10-1. The Miocene, for the non-geologists out there, was between 23 and 5 million years ago. First, let's take a look at today's geomagnetic field. Here you can see the field surface, the field strength at the surface, which resembles a dipole, but not completely. So the non-geocentric axial dipole or non-GAT features are these high latitude flux lobes in both the northern and southern hemisphere, and something called the South Atlantic Anomaly, or SAA, which you can see here is a weak patch over the South America and South Atlantic Ocean. When we look at that same field, so today, the present day field, but at the core surface, you see these same features, but in more detail. So here you can see the radial field at the core surface, the core-mantle boundary, in microtesla, where you can see the high latitude flux lobes and two reverse flux patches under Africa and the Atlantic Ocean that are the South Atlantic Anomaly, but on the core-mantle boundary. Furthermore, you can just see a lot more detail. And it's important to note that this is also more detailed than we could ever show in a model built on paleomagnetic data. And also that you would see in a time average model, which is what we are going to present. So here you can see the Goffin model through time, which runs from 1590 to 1990 AD, which shows that the South Atlantic Anomaly has not always been here. It's important to note that the South Atlantic is right here because the central meridian is the 180-degree meridian in this model. And around 1800 or a bit after that, you can see the two reverse flux patches showing up. So here there's already one, but then around the late 1800s, a second reverse flux patch starts around Eastern Africa. And the two RFPs, or reverse flux patches, move westward towards the location that they have in today's geomagnetic field seen in the previous slide. This is important because it means that the South Atlantic Anomaly has not always been part of our field. So there's not a continuous anomaly in the South Atlantic. Question is there a recurring anomalous feature in that region, or is it a one-off? Studies that suggest it's a one-off also link it to an upcoming reversal, where the North Pole becomes the South Pole in the magnetic field. So it's extra important for us to know whether we're talking about a recurring feature over a long time scale or a one-off situation. The first half of my PhD was to answer that question. We went to St. Helena, which is an island in the Atlantic. It's the red star here on the intensity plot. And we collected volcanic samples that we performed paleodirectional and paleointensity experiments on. In my paper from 2020 in PNAS, we present the directional data, which showed that when looking at the directional scatter, or what we call VGP dispersion, this was significantly higher at St. Helena than what we expected for that latitude based on the global distribution in the last 10 million years. As St. Helena was formed between 8 and 10 million years ago, that suggests that this unstable field that we see in the South Atlantic was a recurring feature on a multi-million year timescale. And not only the directional results show this paper that is in review at the moment at JGR Solid Earth shows similar results, where we show the paleointensity results from St. Helena that are weaker than the average for the Miocene. So what we have shown is that the South Atlantic anomalous features have been recurring on a multi-million year timescale. Question that we were trying to answer with our time average field model is if it's consistently recurring enough and stably enough to appear in a time average field model. We create our time average field model using directional data to solve a non-unique inverse problem of what the morphology of the field was like, which we describe using spherical harmonics. Previous models with these same methods are listed here. So there's time varying models like CALAS 10K, GGF 100K, and all of these models don't go further back than 100,000 years. And then there's the time averaged field models like our own, which don't go further back than 5 million years so far. LN3 is the most recent one, which was presented in 2018 by Cromwell and others, and which we will compare our model to as well. So we add our own model to this list on the right, called M10-1, which is for the Miocene from 23 to 5 million years ago, and therefore the first model going back further in time than 5 million years. To create this model, we needed a lot of data from the Miocene. Paleomagnetic data is not easily found, and we had to go through all the published material to find quality paleodirectional data for our database. We used Scopus, Google Scholar, MAGIC, the Geopaleomagnetic database, and we went through over 1,500 studies to look for the high quality directions from the right age that did not experience local deformation or rotation, so we could trust their declination and inclination. We found 42 studies with 38 different localities, each locality having at least 10 sites. And we corrected our locations for plate tectonics and our Marvel model. Because the Miocene experienced many reversals, as seen in this geomagnetic polarity timescale, we have both normal and reverse data in our data set. It has previously been suggested that the field actually behaves differently during a normal crown versus a reverse crown, because possibly the dipolar component and non-dipolar component come from a different source in the outer core. If this is the case, we need to separate our data and model the field for a normal field and reverse field separately. In this plot where you can see our data distribution of PSVM, our data set, you can see the green localities, which have sufficient sites for all three versions of the data set, so the combined, the normal, and the reverse. The blue localities have sufficient data, so at least 10 sites for the combined and for the normal data set. But when only looking at the reverse data, it has less than 10 sites. For the pink localities, this is the case when looking at the normal data. It doesn't have sufficient sites to be included, but it does get included in the combined and the reverse data set. And then there's a few white localities like 34 and 43 that are only included when we combine the data set between normal and reverse data, because otherwise they do not have sufficient sites to get a good time average field. First, we look at our normal data set and we create our preferred model for MTM1N, so the normal data model. We base this model on 26 localities, each with at least 10 sites per locality. And we use GAD, so the geocentric axial dipole, as a prior model for our model. Then we vary our damping parameter. So the more it gets damped towards GAD, the more it looks like GAD. Here's a trade-off between our model misfit, or misfit squared, and the model norm, or the roughness of the model. So the less damping we have, the better it fits the data. But then after the knee of this trade-off curve, it goes towards such a rough model or high model norm, even though the misfit of the data doesn't decrease that much anymore. So what we're looking for is the knee of this trade-off curve, which is the purple dot, which is our preferred model. The red dot is an overdamped model that we show here, which shows similar features, but it doesn't contain all the robust detail that we can show in our preferred model. And the model misfit is quite high compared to our preferred model. It's higher than 1. And then the green dot is an underdamped model, which shows much more detail than we can say is robust for our model, and that we could expect from a time average field model from paleomagnetic data. What we see in our model is this reverse flux patch under the Atlantic Ocean that could be a sign of the South Atlantic anomalous behavior being continuously recurring and appearing in our time average field model. So first, we compare this normal model to LN3, which is the most recent model for the 0 to 5 million year era, where we see that there are features in similar locations. So the features from LN3 are above Central America, like this reverse flux patch in our model, and above Africa, like our reverse flux patch here. But LN3 does not show it as a reverse flux patch and shows less robust detail in general. So is this due to different data between the last 5 million years and the Miocene, or is it mainly due to the different code or damping? We wanted to test this by using the same data from LN3, but with our own model. So we created LN3 primed, which we damped less to make it more comparable to our own model. There are still features in similar locations that we can see the similarities between. So there is this lobe above Southeast Asia that appears in both models. Again, this is for the last 5 million years, and this is for the Miocene, so going from 5 to 23 million years. And all of these models are on the core-mantle boundary. It's important. And there is a similar lobe across Eastern or Central Asia. But then the reverse flux patch that we see in our model does not quite show in LN3 primed. However, it does show a tendency to go towards a South Atlantic anomaly. So there's a lobe going south that would create a weak field in the South Atlantic. But the LN3 prime model misses data from the South Atlantic, as St. Helena, the island that we researched, is not included in this data set. There is data from the last 5 million years from South Atlantic, from Tristan da Cunha, but it's not included in PSV10 as it was published afterwards. So it would be interesting for future work to see what that data set does when Tristan da Cunha is included. Another important difference is this large reverse flux patch in the Pacific Ocean and LN3 prime that does not show in our model, which is most likely due to a large data set from Hawaii in the last 5 million years, which comes from the Bruins, which is not included in the Miocene data set. So a question to answer is, are these similar features that we do see caused by really robust features in the magnetic field that just lasted over all this time? Or because there are similar data locations, even though it's different data, we still sample from similar locations, as that's where the volcanic eruptions are. When we compare our normal data model to our reverse data model, we again see similar features in similar locations. So again, we have this lobe over Southeast Asia, the reverse flux patch over the Atlantic, and in the reverse data set, it appears not quite as a reverse flux patch, but definitely as a lobe towards the south, and there again towards the north. So the models show up quite similarly. There's a difference in the high latitude flux lobe, which appears here in the normal model, which doesn't appear in the reverse model. But the few differences that we see will probably be explained by the different data distribution. These similarities suggest field symmetry. So what I mentioned before between the field being in a different state during normal and reverse state, so sorry, behaving differently between the normal and reverse state, might not be true if these similarities are actually robust. So to test this, we used MTM1N as a prior for the reverse data set and MTM1R as a prior to the normal data set. So these models are no longer damped towards a gap model, but towards the reverse state model that we came up with, that we produced. Here the similarities are even larger and the difference is even fewer. Again, we see these two reverse flux patches under South America and the Atlantic. And this provides additional evidence that the field is in fact symmetric during the Miocene, and that these reverse flux patches are a robust feature as they show up in all types of our models. Because of this similarity, we decided it would be okay to combine our data sets. So we created MTM1, which is based off our entire data set from the Miocene, so normal and reverse data combined. This increases higher resolution model because there's more data as input. And this model shows us some observations like these robust reverse flux patches in the Atlantic. There is high latitude activity, but there's no clear flux lobes like we saw in the present day field. And another thing to notice is that there's more structure in the Atlantic hemisphere compared to the Pacific hemisphere. Now, this might be due to a higher data resolution in the Atlantic hemisphere, but as Chris showed you in the first talk, during this with the satellite data, there's also higher activity in the Atlantic hemisphere. So it might just be a very robust feature that the Atlantic hemisphere has more secular variation and more activity in the geomagnetic field. Some implications from our observations are that the Atlantic reverse flux patch suggests further evidence of a consistent recurring irregularities in the South Atlantic. And the field symmetry suggests no long-term memory of the non-dipolar magnetic field, which suggests that there's no evidence for a different source for the dipolar and non-dipolar component of the geomagnetic field. To summarize, we compiled a new paleodirectional data set for the Miocene, which is from 5 to 23 million years ago, called PSVM. We used PSVM to create a non-zonal time average field model for the Miocene called MTEM1, which is the first going further back than 5 million years, and is shown here in this plot again. MTEM1N and MTEM1R, so the normal and reverse model, are quite similar, suggesting no substantial field asymmetry between the normal and reverse state in the Miocene. And all of our models show robust reverse flux patches in the South Atlantic, suggesting consistently reoccurring irregularities in the South Atlantic, which is consistent with certain recent studies like our own about St. Helena. And this is all on a multi-million year timescale. Thank you.
Thank you, Elle. Now, we seem to have lost our Q&A facility. Not quite sure why that is. But if anyone's got any questions, then I think I would have to kind of do something to you can try unmuting, but as anyone wants to raise anything directly, we'll get the
Q&A is working for me, Richard.
Aha. Okay, so we have a Q&A. So we've got question from Kathy Whaler. You mentioned the misfit for the first model you showed, but not for the later ones. Are they similar around 1?
Yeah. I figured I wouldn't have to show the methods I use every time, but we use similar method looking for the knee in the trade-off curve, and they all go to close a little bit lower than 1.
Okay, so that was open. Thanks. Well, we will dismiss Kathy's thanks if we can. I don't know how to do that anyway. Does anyone else have any particular question for Yale? They want to kind of wave a hand or shout or ask further. We'll be able to talk more in the poster session in the Gather Town, so that'll work nicely, I think. Okay, so if there aren't any other questions, then what we'll do, I'll hand over to Richard to introduce the poster.
Great, thanks, Richard. So we have a few minutes. The poster session will be in this Gather Town app. I'll show the link to it in just a moment. But first, I want to just give the poster presenters an opportunity to introduce themselves, the title of their poster, so we can just kind of connect names and faces and research together. So I've got it in order here. So Hannah, do you mind leading us off?
Yes, absolutely. Hello, my name is Hannah and I'm based at the University of Edinburgh. I'm currently writing up my PhD. And this is a poster about some of my PhD work, which has been focused on adapting a methodology to look at localized, regions of secular variation and core flow. So really trying to see how features such as these large low shear velocity provinces are affecting flow underneath it. So come and speak to me about magnetic field, regional Slepians, regional fields, yeah.
Great, thank you. And Joseph, do you mind going next?
Sure. Hi, my name's Joseph. I'm a postdoctoral researcher now at the University of Bristol, and I'm presenting a poster on some of my PhD thesis, which is on a new method I've been developing along with James Lockey and Mike Kendall to directly invert shear wave waveforms for the orientation and strength of seismic anisotropy in the lowermost mantle. So yeah, come check out my poster. We've got some results from the joint inversion of SKS, SKS, and SCS shear wave data for some single crystal elastic tensors. Yeah, so come on, check it out.
Great, thank you. And Dan?
Hi everyone, I'm Dan from University of Liverpool, and I've brought a poster about the paleomagnetic signal at the possible onset of inner core formation in the Ediacaran period. So come over and check this out. Back to you, Richard.
Great, thank you. I have some work showing a new update to the PINT database. So if you're interested in paleointensity records going back now to 4 billion years, come talk to me. Or if you have some questions about the session, hopefully I can answer them.
Hi there. So this work is about you combining simulations of the dynamo process and geo and paleomagnetic observations to try and produce theoretical descriptions of the evolution of Earth's magnetic field strength. So we're sort of coupling dynamo theory with dynamo simulations and evolution models for the core-mantle system to sort of learn something about core-mantle evolution over geological time. So come and check it out.
Great, thanks, Chris. There we go.
Mm-hmm. Going to start again, and Paula's going to give a talk. So I'll leave Paula to say her own title and set up and things.
Thank you. I'll just share my screen. Does this show up all right?
Yeah, it looks good.
Yes, good.
Okay, great. Yeah, thank you very much for the invitation to talk today. It's very nicely timed during the sleep of my little daughter, so I can actually make it. So I want to talk about the LSVPs at the core-mantle boundary, as they're commonly called the large low shear velocity provinces or large low seismic velocity provinces. But I've actually dubbed them large light structures and velocity provinces here, because I want to talk about how they might be overall light, but they have heavy details towards their base and in patches within them. And this is work done together with a group of people, very interdisciplinary as well. So some of the work is based on a review chapter I've done. Some work is based with Fred Richards, Mark Hogarth, Sia Galligan, and Harriet Lau. And then some other work is with Alex Roxon, who finished his PhD with Barbara Matovich and Harriet Lau as well. So some things are definitely led by others, and I'm just presenting them. So for decades, we've been imaging these large low velocity provinces, or LLVPs or LSVPs, in the lowermost mantle, below the Pacific and Africa. And we see these few velocity percent decreases, and they reach hundreds or even thousands of kilometers up from the core-mantle boundary. And this is just an example of an S-wave velocity model and a P-wave velocity model. And these are very much, this is a very long wavelength model, so you don't see that many details. We are now seeing many more details in these structures as well. But if we look across a number of tomographic models, we see them very consistently. So these are vote maps based on 12 S-wave velocity models at the top and 8 P-wave velocity models at the bottom, which have all been only developed since 2010. So they're all relatively recent models. And we see very consistently all these the seismic velocity variations with these slow velocities, perhaps in multiple structures, even in these vote maps. But we continue to make a lot of cartoons while we do not know exactly what they are. And so some of the key questions that have been outstanding and have been debated in the community a lot are whether these structures are have low seismic velocities because they are thermal, or whether they are thermochemical structures. Are they piles or plume bundles, either thermal or thermochemical plume bundles? And if they're chemically distinct, is this material primordial or has grown over time? And what is their influence on mantle dynamics? Are they anchoring mantle flow, or are they passively kind of deforming around the core mantle boundary? And we care about answering a lot of these questions because if they are large-scale chemically distinct structures, they would have a pronounced effect on the cooling efficiency of the mantle, effectively blanketing the core from cooling, and that has implications for how we understand the thermal history of the Earth. But also it changes the heat flow out of the core. If these structures are chemically distinct and have been there for a long time, they will be very hot, so we will have a reduced heat flow underneath them, and have quite a strong heterogeneous heat flow out of the core, which has an impact on inner core growth, and possibly time variations in that might have been linked to magnetic field reversals. So understanding whether they are really chemically distinct on the large scales has an impact on several dynamic processes that might influence habitability of the Earth. Now, to unravel some of these questions and to answer them, having constraints on the density of the lowermost mantle and the topography of the core mantle boundary is really important. The density provides the driving forces for mantle flow, and it gives us a snapshot of the present day. But especially if we combine density constraints with velocity constraints, we can start to say something about the origin of these mantle anomalies, whether they're thermal or chemical. And then core mantle boundary topography is, if we have constraints on this, it gives us a lot of insights into dynamics in both the core and the mantle of the Earth. It combined with seismic velocity information, it also helps us to constrain lower mantle density, and it would give us constraints on the mantle viscosity. So I want to, there's two parts to this talk. In the first part, I want to review some of the progress we've made towards our understanding lower mantle density and Cmb topography, discussing whether there's any consistencies between current models and what we might already learn from these. And then in the second part, I want to show work that we've been doing in trying to find density and Cmb topography models that are consistent with a range of data. And I'll introduce that more later on. So in the first part, when I reviewed existing models, I've used these to build average models, which are called R-mean or T-mean, following the methodology of Becker and Boschi. And I've also developed these vote maps, which is following the methodology from Shepard et al. And in these vote maps, the long wavelength components of the models are used. And then a threshold is imposed to extract only positive or negative values that are larger than this threshold, so that they're the most significant anomalies in the models. And this is done for each model, normalized, and then we can combine it with all the models together to get a vote map, for example, for the positive mean. And the number of votes indicates the agreement between the models. Now, this methodology only allows you to analyze existing models. Of course, the resulting maps that we obtain are not true, but we can start to see some consistencies between models. And to get a combined vote map, this methodology is applied to both the positive anomalies and the negative anomalies. And then these are combined to get this kind of combined vote map, which can also be compared to the average models to see how consistent, to say a little bit about how consistent the amplitudes are between the models. Now, when first of all, I show you some results for the density. And lower mantle density is very difficult to constrain, to image, and it's been mostly imaged using normal mode data. These whole Earth oscillations that we have, that we can observe after large earthquakes. But most of the models that have been obtained using normal mode data, they find dense LLVPs, and you can see a collection of these models here, starting in 1999 with the model by Ishin and Trump. And so in the black circles, you see the locations of the LLVPs, and you see how we always have these blue colors in the density field, which are dense LLVPs. but their details differ. So if you look at these models, they're not very consistent. And the relationship with seismic velocity structure also differs substantially. Now, if you look at the two models on the right-hand side, which were both published in 2017, the top model is by us based on Stirling mode data, a subset of normal modes that are very sensitive to the core-mantle boundary. And the bottom model is the model by Harriet, Lau et al. And others based on tidal data. And the methodologies employed between these two studies were very similar, but the results are opposite. And so there's a seeming inconsistency between these two models, because actually the core-mantle boundary topography also has a large influence on this. And it is possible to have compatible models if you allow for different Cmb topography. But overall, these two models are seeming consistent. And so towards the second part of the talk, I'll also talk more about this and how the newer density models that we are coming up with can address this inconsistency. Now, when you use these 6 different models, this is the kind of vote maps and average models that you obtain. So on the left-hand side, you see the vote map, and in red and black, you see agreement between dense structures. And then in the middle, you have this combined vote map, which looks a little bit like a model. And on the right, you have an average model of the 6 models. And so we see that these 3 different maps are very consistent, which means that there's not one model, particular model dominating the results, because then the average model would look quite different, perhaps. And we see these 2 patches of high densities centered around Angola, roughly, and Africa, and around Hawaii. So they're not the full extent of the LLVPs, but they're much more in the core of the LLVPs that we see them. Or for the Pacific one, a bit more on the edge. And when we compare this to some recent work by Liu et al., who also performed Seismodynamic tomography, and you can see their average density on the right-hand side, the locations where we get these dense anomalies under Angola and fits really well with where they found a dense core of the LVP as well under Africa. And so this is kind of suggesting that instead of the entire LVP being dense, these models are showing that there's only a part of the LVP that has a high density, and it's not the entire structure. For the Pacific anomaly, there seems to be an offset between these vote maps and where we see it in this recent model. And that can be due to the fact that in all the normal mode-based models, often even spherical harmonics are used. So this anomaly under the Pacific might not be constrained that well and might actually be shifted a little bit to be more consistent. So I think that the exact location there could be an artifact from that. But we're seeing kind of spatially confined dense areas in the LVPs. Now, coming to Cmb topography, Cmb topography models have been developed for more than 30 years using both body wave observations and normal modes. So for body waves, generally waves have been used that reflect or refract along the core-mantle boundary. And because there's strong trade-offs with structures in the lower mantle, the amplitudes and the patterns in these models vary widely. And here you can see a collection of 10 different models with some of the earlier body wave models and some of the and then on the bottom right are some normal mode models. And you can see that they vary a lot. So again, I applied this, I developed average models and vote maps to try and see whether we have any consistencies between these. And in this, I split out models based on normal modes and normal models based on body waves. So there's only 4 normal mode models that have actually published Cmb topography, and then I've used these 6 body waves, or I combine these 10 different models. And in this case, this is a vote map for elevated topography. So in red colors, you see regions of elevated topography. And when we look at these vote maps, the normal mode vote maps are quite consistent. So these different models are relatively consistent. But when you look at the body waves, the agreement is not very good. We have a lot of blue and yellow areas, which suggest that there's not as much agreement. And also the agreement between normal mode models and body wave models is not very good. So when we combine all of them, we don't have any real consistent regions where we have elevated topography. But overall, we generally see elevated topography in the Pacific and under Africa, so roughly coinciding with the locations of the LLVPs. And I've tried to analyze this a little bit further to look at following this work by Deschamps et al., who used geodynamic model simulations to come up with a relationship between S-wave velocity and Cmb topography and try and interpret that in terms of the scenario for the lower mantle. So in the case of a plume cluster where we have low seismic velocities, we expect an elevated topography, and so we would have a negative correlation between VS and topography, where we define topography positive upwards. Whereas in the case of a heavy thermochemical pile, which is an area on the right-hand side, we would have a low S-wave velocity and a depressed core-mantle boundary, and that would give us a positive correlation. And for a weakly thermochemical pile, where the density contrast is less, we would have a weakly negative correlation based on their simulations. So I've for any model, some seismological model where we have a consistent S-wave velocity and Cmb topography, I've calculated these correlations on the long wavelengths, as the Deschamps paper has done as well. And on the top, in the top kind of part of this plot, are individual models in the background, which are different models based on normal modes and body waves. And in the bottom are bars that indicate the ranges found in these geodynamic simulations. And then the arrows on top are just kind of summarizing these results. So for seismology, in terms of seismological models, we find generally a negative correlation, lower than 0.4, and that corresponds mostly with these thermal or weakly thermochemical models in the simulations, whereas the strongly thermochemical models would have a positive correlation. We also, which I'm not showing here, but all the topography models have a peak-to-peak amplitude that is below 4.7 kilometers on the degree 2 component, and so that could be quite an important, useful constraint for dynamic models as well. And so when we summarize this comparison, we could, with the current models of Cmb topography, which do show inconsistencies between them, we could rule out these strongly thermochemical models, where the density difference between the pile material and the background mantle is about 100 kilograms per cube meter. So that was just summarizing what we know from existing models and what we might learn already from these. And now I want to get to the second part, where we're trying to build models that are consistent with a wide range of data. And just to give some thoughts about how we might build consistent models of lower mantle density. I think it's really important to take an interdisciplinary approach where we don't only combine seismological data, but we make sure to also use geodetic data, such as the observation of the body tides and the geoid, but also geodynamic data, so explicit Cmb electricity and dynamic topography, while making sure that any of the models that we will come up with are geodynamically feasible. And then the density structures that we come up with, we have to make sure that they are compatible with what we expect for mineralogy of the mantle as well. Whereas when we're just trying to find scaling factors, the resulting scaling factors might not be that compatible with what we expect. And we have to make sure that we explore a full range of possibilities, that we don't come up with one model necessarily, but that we really explore the model spaces to come up with a range of possible mineralogies and density structures. And so I want to show results of this work led by Fred Richards, where we're using forward modeling of realistic scenarios and testing these against a whole range of observations. And we're in the process of publishing this, but at the moment you can find a preprint on Earth Archive that we welcome everyone to have a look at and also give us feedback on. So in this work, we our approach is as follows. We assume a mantle viscosity structure, and we use 3 different models, and we assume a density field. And then we use instantaneous flow modeling to get the flow field and dynamic topography and geoid predictions. And we also forward calculate the body weight, body types, and the normal modes. And then we compare these to our observations and make a joint misfit of all the observations. As input models, we use two different sets. In the first instance, we use existing tomography models, and we scale these in different regions. And I'll say a bit more in a moment. And in the second set, we use density models from thermodynamic calculations, where we've used 3 different compositional end members. So for the first set of density input models, we use 5 existing shear wave velocity models, and we vary a scaling factor between density and the shear wave velocity in 5 different layers in the mantle. In one of these models, we assume everything is purely thermal, and so the density structure in the bottom of the mantle looks like something on the left-hand side here. And then we have 2 different sets of thermochemical models. One where we have a different scaling in the LVPs, which you can see on the right-hand side here. And because you're scaling S-wave velocity with density, it generally means that the highest density anomalies are found in the center of the LVPs, where we have the highest S-wave velocity variations. And that might not be that realistic, because they are likely also the hottest regions. And so we also use thermodynamic models where instead of scaling within LVPs, we add a density jump for the LVPs, and that gives us a much more homogeneous density structure within them, rather than this concentrating the anomalies in the center. And so by scaling the density in 5 different layers, we get quite a large number of input structures that we use in the forward calculations. And I'll just show some brief data fits of these before showing the overall results. Here on the left-hand side, you see the geoid in the center of the dynamic topography, and on the right-hand side, you see the excess ellipticity of the Cmb. And the top row shows you the observations. The middle row shows you predictions for our best fitting thermal possibilities, so using the tomography model and the viscosity model that provides the best fit. And in the bottom, the best fitting thermochemical prediction. And what you can see is that when we compare the observations with the predictions, that for the dynamic surface topography and the geoid, we get a similar fit from these thermal and thermochemical models. But for the excess ellipticity, the thermal model over predicts the amplitudes, and only the thermochemical models can give us a good enough fit. If we look at the tidal observations, they are generally better fit by the thermochemical models as well, so they have a higher significance level, over 95% for thermochemical models. Looking at the Stoley mode data in a bit more detail, because that's been more my part of the project. Here you see different Stoley modes on the vertical axis and different tomography models on the horizontal axis, and the color indicates the misfit to the data, with the bottom row showing the misfit of all the combined Stoley modes. And overall, the Stoley modes have the best fit when using S40 RTS, so this red star. But all the geodynamic data are fitted best if we use the Texas 2011 model, which has higher S-wave velocity amplitude. And so when we look at that model, which you can see in the red squares, then we actually get a 20% misfit reduction for the thermochemical model compared to the thermal model. So when using this model, the Stoley modes also prefer these thermochemical structures. Now that was just showing the best fitting model for each tomography, but we can also look at the range of scaling factors that we obtain from this exercise. And so here you see results for the 5 different layers in the mantle. So the lower upper mantle, the upper mid mantle, the lower mid mantle, and the upper lower mantle, and the lower mantle. And the red panels show you the scaling factors that we obtain for the thermal models, and the bottom panels, the blue and purple, show you the scaling factors we obtain for the when the mantle is assumed to be thermochemical. And there's a few, there's like 3 main observations that we want to highlight. So the first thing is that when we look at the mid mantle, so 1,000 to 2,000 kilometers depth, for both cases, we get the best scaling factors of around 0. So we're not seeing any density anomalies about 900, 1,000 kilometers above the core-mantle boundary. So that would suggest that the LLVPs in terms of their density structure do not extend above 2,000 kilometers depth. Then when we look at the lower mantle, so 2,000 to 2,700 kilometers depth, here we don't get a strong chemical anomaly for the thermochemical model. So these purple bars are kind of centered around 0. So we don't have we don't have much of a enrichment in basalt. We have a R value scaling factors of about 0.3, 0.4 still. But these thermochemical models agree better with what we expect from mineral physics. So the little bars indicate the mean or the median and the percentiles, and these black bars indicate predictions for mineral physics calculations. And so these blue bars overlap much better with our predictions. And if we look in the lowest layer, so just 100, 200 kilometers above the core-mantle boundary, there we actually get a density anomaly. So we get about 1% jump off the basal layer of the LLVP. And that is also consistent with the body height data, which I will get to later. But importantly, we're not seeing this higher density throughout the lowermost mantle. We're only seeing this in this 200-kilometer basal layer. So that's based on scaling factors, and that doesn't tell us that much about what the composition of these LLVPs might be. So we've also used some thermodynamic modeling of assuming 3 different scenarios for what the LLVPs might be made of. In one scenario, we assume they have a morph composition if they were composed of present-day subducted basalts. We also assume that they have a chondrite enriched basalt if they more reflect subducted Hadean crust, or and we have a third scenario where we assume they have an iron enriched pyrite composition where there might be the remnants of a basal magma ocean. And these are the density structures that we would obtain from using perplex to calculate the velocity and density anomalies. And what we do in this work is that we vary the layer thickness and the fraction of the dense material that might be present within the LVPs, and we assume a pyrrolite composition outside the LVPs. And then for each possible model with a particular layer thickness and the fraction of the dense material, we compute the fit to all the data again, and we can look at some trade-offs between these layer thicknesses and the fraction of the dense material. So just to show that for the Stirling modes, here you can see an observation for a particular Stirling mode, 2S16, which has the sensitivity shown here. So the sensitivity to S and P wave velocity and density peak in the lowermost mantle. And here you can see predictions for 9 different models where the fraction of the dense materials varied along the horizontal axis, and the thickness of this dense layer is varied along the vertical axis. And so thick layers are at the top. Purely thermal models are on the left-hand side, where there's 0% dense material. And then very dense material models with very dense material are on the right-hand side. And when you compare these to the observation, you can see that there's a range of models that fit very well. And we see a trade-off between the thickness of the layer and the fraction of the dense material. So models roughly around this line would be fitting very well with the observation. So we do this. We can do this for all the different modes together and plot a misfit surface. And you can see them here for these 3 different compositions that we assume, and we have the same axes. So thickness of the layer on the vertical axis and the fraction of the dense material on the horizontal axis. And we can see this clear trade-off between the thickness of the layer and the fraction, where we get we get good fits if we have a thinner layer with a higher fraction of dense material, or we could have a thicker layer with a lower fraction of dense material. The red dot indicates the optimum model. So mostly we're getting better fits if we have a thin layer that is more dense. Now this is for the Stirling mode data, but we can also do this for the different geodynamic data sets. You can see the misfit surfaces here, where we actually get a very similar trade-off as well, and also optimum models are found for thinner layers with more dense material. So we can combine the different data sets together in a combined misfit, and so these are our final misfit surfaces, where the red region indicates the best fitting models. The hashed region indicates models that do not satisfy this criterion that the degree 2 component of Cmb topography is larger than 4.7. And on top, we plot these blue contours, which indicate the density difference between the dense material and the background mantle. And the blue shaded area then indicates the region where this is larger than 2%. And we use this as a threshold based on geodynamic models that suggest that we need a 2% density anomaly to ensure long-term preservation of any dense material. So if we take all of that together, the possible models fall in this blue shaded region. And so we find models that have about 200 kilometer thick layer of dense chemically distinct material. And that's compatible or consistent with some geochemical constraints, a particular recent study of tungsten isotopes, which suggests that the isotopes in oceanic island basalts have to come from the deepest parts of the mantle, so from such a basal layer. And the overall lowest, so we don't necessarily want to discriminate between the different compositions, but we do get the lowest misfits for these chondrite enriched basalt compositions. So perhaps that is the most compatible with the data, but all three give similarly low misfits. And this concept of these dense basal layers is compatible with both the body tides and the Stirling mode data. And I just want to expand on this briefly. If we consider the sensitivity kernels of the body tides, which you can see as a summation of about 10 of the longest period normal modes, these are the sensitivity kernels within the solid line, the sensitivity to density, and this sensitivity peaks right at the core-mantle boundary. Whereas if you consider one particular Stirling mode, the sensitivity to density actually peaks above the core-mantle boundary, about 200 kilometers above the core-mantle boundary, and the sensitivity right at the core-mantle boundary is much lower. So the tidal data are sensitive to the deepest part, and the Stirling modes are sensitive to structures above it. So perhaps it's then not surprising that we are finding low densities with the Stirling modes, which are mostly seeing the structures above this basal layer, and high densities with the body tides, when we're seeing mostly this deepest part of the structures. So this is not, these data sets are not inconsistent with each other anymore, and we can resolve this discrepancy. So to summarize these findings, we find that we have there must be a balance between the thermal and chemical anomalies that leads to dense structures just being present in the basal parts of the LVPs. However, whether this is actually present as a basal layer or more patchy is difficult to say based on these data sets that we used in this study, because all of them are sensitive to long wavelength structures in the lowermost mantle. And so it would not be inconsistent with this recent work by Liu et al., where they have more patchy dense anomalies. I think that is compatible with each other, given the sensitivity of all our data sets. And then, of course, it's possible that instead of this being a large structure, with the like I've drawn it here as a cartoon, that actually they are just thermochemical plume bundles, as also suggested by Andavai and Romanovich in their study last year, where these dense patches occur at the bottom of these thermochemical plumes. And we are now in tomography starting to see these structures in much more detail. So we shouldn't think of them necessarily anymore as these long, big wavelength structures. And so coming back to some of the questions that I mentioned at the start, well, I think we are converging on scenarios where these structures are thermochemical, but they are not, as the early normal modes models suggested, they're not big thermochemical piles of 1,000 kilometers thick with a high density. They're much more of a balance with the high density only in the basal parts and perhaps only in patches. And of course, geochemistry requires that some of this material is primordial, but from our work, we can't necessarily distinguish between the three different compositions. And I think what will be interesting is for geodynamicists to test some of these models where we have dense material only in patches, because still relatively often we have dynamic models where we have big thermochemical piles. And we now need to have more dynamic models where we only have dense material occurring in patches at the right locations and see how they compare then to seismology. So if you want to read more about what I've been talking about, you can look at the review chapter, and the float maps and the Everest models are also online. And you can look at our work on Earth Archive, or this study where we're analyzing sterling modes in more detail, which is in press for GJI. So thanks for listening, and I'm happy to answer any questions.
Okay, I can quite happily lunge forward with questions, but that would be self-indulgent even by my standards. So is anyone else there first who would like to ask something? And if no one jumps quickly, well, there's a Q&A, or there's a couple.
Oh, there's a few already.
Yeah. So Paula, do you want to kind of attack some of those? Probably Andrew Walker hasn't had anything to say yet, so maybe not with him.
So Andrew asked, do the calculations giving density from the modes and tides capture the effect of Cmb topography? So in the second part, where we're trying to combine all the different data to get models for density and Cmb topography, we also calculate Cmb topography from the instantaneous flow calculations, and then that topography is included when we do the forward calculations for the normal modes and the tidal data. So could upwarping of the Cmb result in some contribution of the core density show up in the mantle density just above the core-mantle boundary? I think not. When we're using perturbation theory with the normal modes, and we're seeing it as deviations on the boundary with the density being above it or being the mantle, or below it the core density. So I think it should be accounted for in the way that it's done, that the core density is raised in particular regions above below the LVPs. I think that should be accounted for when we do this as perturbation theory.
I suppose there's a physical issue here as well. We've had ideas of sedimenting stuff on the core side, which then becomes a different kind of thing, and whether it's the mantle or the core becomes kind of semantics almost.
Yeah, I guess it becomes
if it's solidish, then
is the area core? Is it core or is it mantle in some way? Whereas we do need to have a boundary which we perturb in the way that we do it. Yeah, it's interesting to think about more. I know there are people developing other methods where we don't use perturbation theory, and that's probably, those are kind of interesting scenarios to test in those methods where we don't necessarily use perturbation theory of the boundary, where we actually parameterize the Earth model and see how it would affect, how it compares to using perturbation theory, whether that's actually capturing such effects.
Okay, do you want to try Hugh?
Yeah, how important is post-frost guide? So when we do the thermodynamic calculations to get the compositional fields and the density structures in the last part of the work, it's included. So it's included in the thermodynamic databases. There's a big debate, of course, about what the stability field of post-frost guide actually is, whether it's stable enough in the LVPs as well, if these are very hot. And so we include it, and in some of these databases, it means that post-frost guide actually occurs within the LVPs as well, which can contribute to having a higher density in the basal part. We haven't studied in detail how it might affect it if we use the calculations where post-frost guide wasn't included. But in this work, it's just included. When I looked in my earlier work, when I looked at scaling factors, we did see that if you have post-frost guide included, the scaling factor between density and S-wave velocity can actually be higher. So it can be 0.75 even instead of 0.4, which is often assumed for terminal variations. So you can have a higher scaling factor with post-frost guide present. And in our case, that actually explained our density structures more, which is why we argued that post-frost guide was present everywhere.
Okay, and is worrying about plume clusters?
If they are plume clusters, why are lips mostly seen at margins? I guess they are. I mean, it's coming to the question what is determining the location of upwellings, and is it the LVPs determining where these occur, or what are they? Do we see them in particular locations because of the subducting material driving an upwelling return flow? The whole debate about whether they are significantly seen above their margins or not is there's been quite a bit of work debating this. My understanding is that as long as the subducting flux material has been in the locations of the last, where we've seen it in the last 200, 300 million years, we are going to get upwellings that are roughly around the margins or the location of the LVPs, but whether they're statistically better correlated with the margins, I know has been debated. But I think in dynamic models, they can reproduce this.
Okay, thank you. I will grab a quick question for me if I can, because I can't put it in the things. So I probably missed something going through, but you've had your basal layer. How thick is your basal layer?
So we vary that basal layer. In the first part of the density, in the first part of the second half, it's we have a different scaling factor below 2,700 kilometers depth. That's like 190 kilometers. In the second part, we vary the thickness of the basal layer between 0 and almost 1,000 kilometers. And so we then find that the best fits are for basal layers. This is the upper boundary of the dense layer. So we get the best fits for layers that are about 200 kilometers thick.
200, okay. But
it's varied.
Geomagnetically, I'm looking for kind of layers at the Cmb that are thin. So the 200 is even a little bit thick.
So it's only within the LVPs, it's not global.
Okay, yeah. But if we're looking at these kind of effects, there's a kind of, a degree zero effect, which might be. But so sounds like it doesn't answer my. I have to find some. There are many other mechanisms I can seek, so that's fine. So we got about 2 or 3 minutes left. Does anyone else have a question for Paula at this point? If not, then let's move on. So the next talk is to be given, well, for SEDI history, I should ask him for a 20-minute announcement. But instead, it's going to be on regional stratification in geodynamo simulations. And John, I will make an appearance at about 16 minutes. So when my face appears, it's as horrific as it usually is. So it says you've got to finish.
Fair enough. Just check that people can hear me and see everything okay.
Yep, all good.
Right. So yeah, thanks. So this is carrying on some work that I've been doing primarily with Chris Davies, but also some others on regional dynamics at the top of Earth's core. In particular, these things that we've been calling regional inversion lenses, places where convection at the top of the core is likely suppressed by what's going on in the mantle above. And so there's been a lot of work studying what's happening at the top of the core, and there's been suggestions at the top of the core might indeed be stratified. That's come from seismic data, where relative to PREM, many models find that the top of the core has anomalously slow P-wave velocity. There's also suggestions that some of the geomagnetic oscillations could be explained by waves in a stably stratified layer. And so there's a number of reasons why people might think that there's a stratified layer at the top of the core, and there's a bunch of mechanisms that have been proposed to explain how you would form such a layer. It could be primordial from the formation of the core, or it could be something that has grown through time as light elements accumulate at the top of the core, or are transferred down from the mantle. And as the seismic data suggests that such a layer should be strongly stratified and relatively thick, so a few hundred kilometers in thickness. But that's a bit of a problem when it comes to matching observed features of Earth's magnetic field. As Chris talked about this morning, we have various structures at the top of the core. So this is radial magnetic field at the core-mantle boundary. And if you have a dynamo model, you can have that sorts of structures at the top of the core. But as you include increasingly thick or strong stratified layers at the top of the core, you can see that the structures in the magnetic field in these dynamo models, and this is some work from Thomas Agustin, who's done a bunch of models looking at lots of different stratified layers at the top of the core in dynamo models. And you can see that as we get to these layers, the radial magnetic field at the top of the model becomes weaker and longer wavelength. And so you blur out this small scale structure, well, small scale structure, and you get weaker magnetic fields, which don't look very much like what we see in the Earth today, or indeed what we see at the Earth when averaged over, say, the last 400 years. And so this is now a slightly longer wavelength view of what's going on in the radial magnetic field. Again, this is actually a sort of present day field. I just filtered to only show the longer wavelength features because that's what we tend to compare to. And then this is some sort of quantification of different geometric aspects of Earth's magnetic field and how these dynamo models of Thomas fit that field as he increases the effective thickness, or they increase the effective thickness of their stratified layer. And so things like the relative power between the axial dipole and the non-axial dipole, if you have no layer or a very thin layer, it's fine, which is to say it's within this blue band. But as you increase the thickness, the models no longer fit. And in general, for these 4 different measures of structure of the field, 3 of them tend to fail once you get layers thicker than about 50 kilometers. The only one where they can do okay is this one here, which is sort of how concentrated the flux is. So they still sort of can get patchiness in the field that looks sort of Earth-like, but in terms of the other parameters, they don't do well, and overall they would be considered not good measures or not good matches to the geometry of the field. So it's sort of outside this blue band of acceptable parameter values. And so the seismology wants layers that are 200, 300 kilometers thick. And this set of dynamo models suggests that if you have those sorts of layers in the Earth's core, you will not get a magnetic field that looks Earth-like. So that's sort of a preamble to some of the problem that we're trying to resolve. As we've just heard from Paula, there are other things going on in Earth's mantle. We've got these large low velocity provinces, which are some amount thermal, some amount chemical, but at least some amount thermal, which means they are hotter than the average mantle, which means that in terms of the heat that they extract from the top of the core, they extract less heat from the top of the core. And so this is a sort of a map of heat flow across the core mantle boundary, sort of taking a seismic model and some mineral physics to work out what the heat flow should be. And you can see that underneath these large low velocity provinces, the heat flow is low. In other regions, the heat flow is higher. And so if we're extracting variable amounts of heat out of the core, then the dynamics that we might get in the core might vary between these regions. And in particular, depending on the exact balance of the heterogeneity of Cmb heat flux to total Cmb heat flux, you might be able to greatly suppress or even shut down convection at the top of the core underneath the large low velocity provinces. And so that's the sort of thing that we were interested in looking at, is how big might those effects be, given that we expect there to be large variations in Cmb heat flux. This is not, we're not the first people to look at this sorts of problem. Many other people have included these sorts of effects in their models and have seen different impacts on both the magnetic field and things like predictions for what you might see for the structure of the inner core. In particular, some of these earlier models found that including this lateral variability in Cmb heat flux led to these patches of high intensity at the core mantle boundary, which look similar to some of the patches that we can see in the relatively modern magnetic field for the Earth. Although the question of how do they persist through time needs more data that stretches further back in time. And one of the other things that these earlier models found was that if you turned up the heterogeneity at the core mantle boundary too much, you would actually damage your dynamo process, and you would cause the dynamo to fail. And so they would suggest that you shouldn't have too strong heterogeneity at the Cmb. But one of the problems with those earlier models is that due to computational constraints, they tended to run not in the parameter space that we think is relative to the Earth. So for dynamo models, we've got the Ekman number is an important control parameter, basically how important is viscosity relative to rotation. And in the Earth, we believe it is a very small number, so way off actually to the left of this diagram. And then we've got the Rayleigh number, so how strong is the buoyancy driving, which in the Earth we believe should be relatively high. And so the previous models tended to fall not in the sort of green region, which is where we think the Earth falls, where the Earth is rapidly rotating and strongly driven. And so we targeted that region with our models. We've done a bunch of work on non-magnetic models to try and understand how these regions behave and where the boundaries between them lie, so that we could sort of focus in on the region in parameter space that we think is most relevant to the Earth. And so those are the models that we will look at today. And this is some examples. This is actually a non-magnetic model looking at convection. So this is temperature in the equatorial plane. And just so you can see, there's lots of sort of small scale convection going on, lots of small scale plumes originating at the inner core boundary and working their way up to the core mantle boundary. And in this case, we have a homogeneous model, so there's nothing particularly different regardless of where you're looking in the Earth. Whereas if you now impose a strong heterogeneity at the core mantle boundary, we can see that there are differences. And so the Pacific is over here, Africa is over there. And you can see that the Pacific large low velocity province in this case is sufficiently hot, that the heat flux is sufficiently low, that the fluid at the top of the core does not cool, and you have this pooling of hot fluid at the top of the core, which sort of shuts down the convection, so you don't see all of these small scale plumes. There's lots of small scale convection happening sort of at the edges of this region, so in between the Pacific and Africa, but not under the Pacific itself or so much under Africa. At depth, things still look like they're going on more or less unchanged, but certainly as you get towards the top of the core, you have these lenses of fluid accumulating under the large low velocity provinces where things are anomalously hot and the thermal gradient is sort of inverted, so things are getting hotter as you go up, which is sort of the opposite of what you'd expect. So lenses of inverted temperature gradient, so regional inversion lenses. And so this is what we see in terms of what the convection looks like. And this is just, we've run lots of models to see in the non-magnetic cases to see how these lenses form. And basically, as you move to higher Rayleigh numbers, you tend to form these lenses of stratified fluid in lots of different models. And they can be sufficiently large and strongly stratified that they dominate the 1D average, in fact. And so we've got lots of reason to believe that this is not a quirk of the particular conditions that we happen to choose. Lots of models with different conditions have these features. And so what do they look like in terms of what we might be able to observe? And so one of the things that we might be able to look at is the flow. And so this is the flow in these models, or one of these models. And you can see that between the large low velocity provinces, between these regional inversion lenses, there's lots of small scale convection going on. So lots of upwelling and downwelling on relatively small scale, with some regions where there's downwelling tends to be promoted, some regions where there tends to be a balance of upwelling and downwelling materials. And then underneath the large low velocity provinces themselves, that small scale convection tends to be suppressed, and there's mostly just sort of a passive upwelling here in the Pacific, and again, under Africa. And so that's the radial velocity. And then we also have variations in the azimuthal velocities. And so eastwards and westward flows in various places. So the purples being sort of westward flows, and the orangey colors being eastward flows. And these are sort of in the time average flow, or the sorts of things that you can see. And so that might then show up in, say, secular variation differences. So as I said, we want to see what that looks like in terms of what does it mean for the magnetic field, which is the thing that is most directly observable from these models, or might be most directly observable for the Earth. And so again, we've got sort of what the present day field looks like on the left, and some models on the right. And my ability to move my cursor seems to have broken for some reason, which isn't great. Let's try that again. And so on the top, we've got a dynamo model that's a homogeneous model. And so you just see, this is time average radial field at the core-mantle boundary. And so we see just sort of a dipolar field. And as you add in increasing Cmb heterogeneity, you can see that there is a bit of non-axial or structure in the fields. We get high latitude patches, different than in previous cases. So this is looking down at the Pacific, and we're seeing sort of two patches sort of on the Pacific hemisphere, rather than sort of the four patch view that some of the earlier models shown. This is time averaged over tens of thousands of years. These are now sort of more snapshots. So 400-year averages, something more similar to GeoFM. On the left is actually still just a snapshot from one instant in time. But you can see that sometimes we get things that do look indeed very Earth-like. So the top model looks quite Earth-like in its structure. The bottom model looks less Earth-like in its structure. It has these very intense concentrations of flux occurring, in this case, 2 in the northern hemisphere and 1 in the southern hemisphere, which is different than what we got in the layered case. So in the layered case, right, as we got stronger stratification, the models failed to fit the Earth. Here, we can have strong stratification as long as it's regional, and we sort of average the thickness of these regional inversion lenses, and the sort of average thickness of the lenses can be a couple hundred kilometers, and the field still look Earth-like. And so the Gastine's results are now in the stars, and our results are now in the other symbols. And you can see, depending on exactly which model we have, we can get sort of effective thicknesses, so sort of average thicknesses of the rills of up to about 200 kilometers, and still do a good job of matching most of these parameters. The one that we tend to have the hardest job doing is matching this flux concentration factor, as we saw in that snapshot before. We have these really strong flux patches that don't look particularly Earth-like. But of course, this varies through time. These models are dynamic, and so in some sense, all of the models that we've run, well, not all of them, but most of the models that we've run will have periods where they do a very good job of matching Earth's field, and sometimes do a very bad job of matching Earth's field, but can vary between the two. Some of them almost always do a good job of matching Earth's field. Some of them, as I say, vary back and forth, and some of them basically never do a good job of matching Earth's field. But certainly we can have strong heterogeneity and Earth-like fields most of the time. And so there's no problem with having a thick regional inversion lenses and matching, sort of some of these characteristics of Earth's field. Talked about the high latitude flux patches, which people have looked at before. It's also worth noting that these models have structure at equatorial latitudes as well. And so we see a tendency to have a sort of a pair of reverse flux patches under the Americas and a pair of reverse flux patches under the Indian Ocean, which are not there in the homogeneous model. But these only tend to show up once we take an average over enough time, tens of thousands of years. They're not particularly noticeable in a shorter, few hundred year snapshot of the field. And so that would be something that might not show up geomagnetically, but might show up paleomagnetically. And so that is sort of a summary of the things that we've looked at. So we run dynamo models with strong CMB heterogeneity. We get these stratified lenses under the LLVPs, which we call regional inversion layers. There's time average signatures in both sort of the flow and the field. If you scale them to Earth, we still expect them to be thick, so on the order of 100 or 200 kilometers. We get flows that look somewhat like the eccentric gyre that Chris talked about earlier, and various patches both at high latitude and some reverse patches in equatorial regions. And we think that this might be a way to have both seismic observations of something thick and anomalous at the top of the core without breaking the geomagnetic constraints in terms of what the Earth's field looks like. And I can see Richard's face, so I will stop there. Thank you.
Thank you, John. Okay, so in the question and answer, Yufan definitely has priority for his question on the grounds he's still awake, which is absolutely stunning. So nothing against John, sorry, just against time zones. So John, could you address Yufan's question?
How large could the temperature gradient be? So I've not done the scaling yet for the dynamo models. In the non-magnetic models, they were, closing in on a Kelvin hotter in sort of at the top relative to their surroundings. So a Kelvin per 1,000 kilometers ish would be sort of the gradient. But it might be different in the dynamo models, and it also might be different in a thermochemical model. These are thermally driven dynamos, so we don't have any of the chemical components from the inner core boundary that might also be important.
Okay. If there are no additional questions at this point, then we will move on. Unless I've missed something. No, I think I haven't.
Okay, then I can share my screen, I suppose.
That would be good.
And I should just start, I suppose.
That would also be good.
Okay, good. So I guess I should change the title of this presentation based on the recent paper in Science Today that was then describing this thing found in a natural diamond, and they've named it Daymar White. So that's the previous calcium perovskite. But I don't have time to change my figures, so I'll just use the old figures that I have. And then I use these mineral abbreviations here, calcium perovskite, CPV, bridgemanite, and I use actually post-bridgemanite instead of post-perovskite. And then ferropericlase, those are the main mineral abbreviations that I will be referring to. So calcium perovskite may be a very major ingredient in the ultra-low velocity zones and also in the LLSVP base layers. And this will essentially solve what I will call the petrogenetic ULV-Z paradox. I'll refer to that in the next slide. And then it will also exclude ultra-low velocity zones and LLSVPs as primordial like helium and solar neon reservoirs, because calcium perovskite is very rich in uranium and thorium, producing radiogenic helium and nucleogenic neon. Sorry, doesn't it work now? Let me see. There it is. Okay, sorry. So the ultra-low velocity zones may be partly open windows to the outer core because, for one, most of the major plume conduits rise from the ultra-low velocity zones, and the deep-rooted plumes have fluxes, essentially plume flow fluxes, correlated with core signals in the form of negative 182 tungsten anomalies and also high 129 xenon to 136 xenon ratios. And also they have also then ancient refractory mantle signals. Some of them at least have positive 142 neodymium anomalies, and they have generally primordial like helium and solar neon compositions. So then I'll present already now just a preview of the consequences and conclusions. So that is that the ultra-low velocity zones in partial equilibrium with core metal and silicate melt cannot contain ferromagnesium, silicate, and oxide minerals with high iron or magnesium ratios. And this is what I call the petrogenetic ULV-Z paradox, because very many people have suggested ferropericlase, post-perovskite, post-bridgemanite, and bridgemanite with high iron or magnesium ratios as candidate materials for the ultra-low velocity zones. And I think that's not workable. Then the conclusion kind of is that high density, which I will show, calcium perovskite, which also is the most refractory mineral during partial melting of basaltic recycled-oceanic crust, is a very suitable ultra-low velocity zone gradient ingredient, together with minor silicate melt and tiny metallic melt fractions. So Earth has produced an oxygen undersaturated core during cooling. And this is illustrated nicely by some experiments done by Otsuka and Karato, showing that metal alloys, they have a metal here in equilibrium with a single crystal ferropericlase with this initial composition, which is rather iron-rich. They see that they get these worm-like structures of metal intruding into the ferropericlase, sucking in the FeO component. producing then a much less iron in the ferropericles, indicated by these red colors. So this has also been shown at very high pressure and temperature. For instance, a summary paper, synthesis paper by Frost et al., showing that this is a thermodynamic model showing the oxygen content in the metallic core versus ferropericles magnesium numbers. And essentially at about 4,000 or 3,000 Kelvin, this is the Earth's assumed oxygen content in the core, and that would produce a completely almost iron-free ferropericles with magnesium number of something like 99. The same is seen for bridgemanite. Bridgemanite also is a pure MgSO3, no iron almost, in equilibrium with core compositions, for instance, estimates for Earth and Venus core compositions. So the implication of this is that iron metal and bridgemanite metal equilibria demonstrate a strong tendency for FeO partitioning to an oxygen undersaturated core. And this, of course, is limited by solid state diffusion, so therefore the mantle cannot really equilibrate fully with the core. But if you have metal, liquid present, then that's a possibility that you have more equilibration. And the second point is that relates to the iron or magnesium partitioning between bridgemanite and melt, and also between post-bridgemanite and melt. And then we express this as the KD for mineral melt partitioning of iron magnesium ratio, which is iron or magnesium in mineral divided by iron or magnesium in melt for bridgemanite and post-bridgemanite. And as you can see, this KD drops from about 0.5 to about 0.1, going from about 24 to about something like 80 GPa, and it might be constant in this 0.1 range throughout the rest of the lower mantle. Then we see that post-bridgemanite appears to have an even much lower value of something like 0.3 to 0.5. So this means that partial melts have 10 to 25 times higher Fe over Mg ratio than bridgemanite and post-bridgemanite. Just wanted to remind you about the mineralogy of the peridotite and basalt compositions. So if you go from and look at the proportion of calcium perovskite, which is less than 2% in a composition like a depleted peridotite, going to about 6% in fertile peridotite, and up to about something like 25 to 28 or something in basaltic composition. And what is melting in the deepest mantle is probably basalt. It probably has a somewhat lower solidus than peridotite. So then the phase relations involving calcium perovskite is first of all demonstrated by this very high and rising melting curve of calcium perovskite, demonstrating very high thermal stability, increasing strongly with pressure. And then I would like to show this in a little bit more complex system, the pseudo-ternary system CMS, where I grouped calcium and sodium as C, and then M then is magnesium plus iron mainly. S is silicon plus aluminum. So this is the lower part of this CMS system with calcium perovskite here, bridgemanite here, silica and ferropericles. And you can see this evolving from 24 GPa via 31 to 136 GPa, the core mantle boundary pressure. And what we see is that the liquidus field, primary liquidus field of calcium perovskite expands enormously from this position to this very wide field at this position. And you can see that at 24 GPa, basalts are almost co-saturated with calcium perovskite and stishovite, whereas at 136 GPa, basalt is far inside the calcium perovskite field demonstrated, and this is the most refractory mineral in the lowermost mantle during basaltic protolith melting. So I'll skip this now and then go straight on to summarize the density relations, which we have determined by ab initio computations. So then instead of, if I have time in question period, I can show the figures if you're interested, but I'll just summarize here and say that the calcium perovskite is denser than the residual Seyfertite, which is the silica phase, and post-Bridgmanite with relatively low iron over magnesium ratio, which is dictated by the equilibrium with a small amount of metallic melt and a larger amount of silicate melt. Calcium perovskite is less than pseudo-eutectic silicate melt, which has a very high iron over magnesium ratio, and that ratio will ultimately sink towards the bottom, but it might be suspended as interstitial melt in the grain matrix by convective movements in the in the ultra low velocity zone. And also the aluminum-rich calcium ferrite structured phase has similar density to silica, but this is kind of irrelevant because this is also the first mineral to disappear during basaltic melting, and there is probably no residual portions of this aluminum-rich calcium ferrite structured phase. So then I'll just show you our model. So this is a blown up picture of the core mantle boundary near the margins of the LLSVPs, which might consist of possible base layers with iron-rich post-Bridgmanite and calcium perovskite, essentially cumulates from the basal magma ocean. And then most likely there is some recycled oceanic crust piled on top of it, or it might be possibly only recycled oceanic basalt composition. And this is, as Paula was saying, if you have a thickness of about 200 kilometers, I think approximately this scale, which I've drawn in this diagram. In the lateral flow along the core mantle boundary, we have post-Bridgmanite everywhere, probably because new determinations of the Clapeyron slope from Bridgmanite to post-Bridgmanite are so low, relatively lower than some of the experimental studies, that this double crossing is probably not happening. So we have post-Bridgmanite to the very bottom. And post-Bridgmanite is the very, very weakest mantle phase of all the minerals in the mantle. And this should ease the flow and make a low viscosity for this region. And that might enable these lenses of post or recycled oceanic crust to sink, because these are basaltic composition, and basaltic compositions are a little bit denser than ambient peridotite compositions, especially depleted peridotite, which is even lighter than a pyrolytic composition. So they are likely to sink a little bit and might be very close to the core mantle boundary, might be enriched a little bit close to the core mantle boundary region. And of course, this is the hottest region. They come from subducted areas in the high velocity circumpolar belt, and they're heated as they flow along the core mantle boundary. And they reach possibly the melting, the soldier's temperature for basalt in this region here, and you form partial melts that is extracted downwards, because partial melts would certainly be denser than any residual phase, any residual solid in this area. So I'll blow up this little square here and take a look at what it might be then at I blow up of this square, then there will be partial melting. And the first partial melt that will form is a small degree of metallic melt. And this is exaggerated in these figures because it's otherwise it wouldn't be visible. Then a larger scale or larger degree partial melt of silicate composition would also sink together with metallic melt. As I mentioned, calcium perovskite is denser than residues of post-Bridgmanite, and then minor Seyfertite, the silica mineral that will presumably rise or could at least presumably rise from this disaggregation zone of the partial melting region. So then you enrich calcium perovskite, and of course the metallic and silicate melt sink downwards. And I'll also look at a small blow-up area here near the core mantle boundary, or at the core mantle boundary. And there are two separate expanded figures. here showing kind of the grain scale, cartoon-like grain scale. And this then would include mostly calcium perovskite with interstitial silicate melt and tiny fraction of metallic melt. And of course, there would be some trapping. Maybe I should have more of these crystals of post-Bridgemonite and Seyfertite here, but there will clearly be some crystals that will be trapped in this sinking calcium perovskite on the way down. Importantly, the core mantle boundary itself, which is this D figure here, that will obviously be a convergence area between this interstitial melt coming from above, from melting of recycled oceanic crust, and the core metal itself. And you will obviously then have a possibility if you have convection here, and that convection is shown here. The sense of convection in the ultra-low velocity zone must be approximately like these white arrows are showing, because you have the flow along the core mantle boundary in this direction, and then the flow is partly dragged with that in the ultra-low velocity zone. And also the flow within the LLSVPs will also be the opposite sense towards this marginal zone. The LLSVPs, as Paula was mentioning, are probably hottest in the middle, or I'm not sure if you said that. I can't. Also, then you have also density, high density there maybe, but regardless, there will be a flow towards the cooler outer margins of the LLSVPs. So this is the sensor flow, and this might enable core sampling of deep plumes rising from this region here. So as these arrows show, you might have a possibility of entraining some small amount of crystal mush with core metal, explaining this tungsten anomaly, for instance. So then I think I will stop there and open for questions if there is time. I just put up these same consequences, conclusions.
Okay, there's a good time for questions, and I think we have a strong desire to ask questions from Christina Hauser. So if you could have a look at the Q&A.
Okay, I'll see.
It's in the chat, Richard.
Oh, it's in the chat.
Yeah, well, yeah, exactly. I see it here. Questions for Reidar. What is the petrodynamic ULV set paradox? Why can't the high iron over magnesium ULV set be in equilibrium with high oxygen stratified layer on top of the core? Yes, if the layer on top of the core had more than about between 15 or 20% oxygen, then it would be okay. Then the core would be saturated in that upper layer. But there is no way of explaining so high oxygen contents in the core from the seismic signature of the core, I think. But of course, it could be a thin stratified layer that was saturated with oxygen. Then this thing would not be a factor. Then the core would not be oxygen undersaturated. But still, the partitioning to silicate melt is very strong, so that will also dictate that if you have partial melting in the partial melt in the ultra-low velocity zone, the iron would be strongly partitioned into the melt 10 to 25 times the amount in post-Bridgemonite and ferropericles. So I think that answered that question.
So there are, was that all three of the questions, or?
Yeah, okay, there are more. If partial melts from the mantle are draining into the ULV sets, then ULV sets are growing larger with time. How to avoid runaway growth? I think that this is, I look at the ULV sets as a dynamic, continuously evolving region that is as is interacting partly with the core, so the melts will ultimately drain to the bottom of the core, and continuous equilibration with crystals would actually make the silicate melt possibly neutrally buoyant. If you have too much crystals that give off iron to the melts, they might actually start to rise again also, and you have continuously replenish the ULV sets by partial melting of basaltic material. That is our model. Should I go to the last question also? There is one more. Geochemistry.
If you can do it very quickly, I also have a quick question.
Okay, yes.
So my question is right from this, and I might have missed this. I've gone zonked a bit, but you talked about radioactive sourcing, radioactive heating due to the post-perovskite.
No, not due to post-perovskite, due to calcium perovskite.
Calcium perovskite.
Yes.
So where is that located?
The calcium perovskite is the main ingredient, the main silicating, the main solid ingredient in the ultra-low velocity zone. That's our hypothesis.
So I'm just thinking about putting sources of heat just above the core and what that might do to core dynamics.
I think that I mean, if I were speculating very briefly without thinking too much, I would say that the core is a greater heat engine than the even small solid. But of course, it would limit the core flow in the areas of the ultra low velocity zones. But they are relatively minor, I suppose. They don't cover the entire surface of the core, but of course it would limit the core flow of heat, as shown by the speaker before, or one of the speakers before me, that shows that the LLSVP flow, heat flow from the core to the LLSVPs is much lower than the heat flow to the high velocity sinking belt in the mantle.
That was precisely my thought. And I think, Christina, we're probably running out of time to do your last question. So maybe can answer offline.
I can answer in the chat or by email. Yeah. I can copy this and chat. Okay, thanks.
And thank you very much. And then so we'll move on to Stuart Russell.
Hello, can you hear me?
Yes, a little bit broken, but let's try again. I can see the screen, which is good.
Fantastic. This is all good news. Can we see this and can we hear me?
Yes, to both. Off you go.
Okay, awesome. So today I'm going to be talking about some work that I've been doing during my PhD at the University of Cambridge with my supervisors, Sana Kotar and also Jessica Irving at the University of Bristol. And I'm going to be talking to you about seismic visibility of melt at the core mantle boundary from P2KP diffracted waves. So why might we think that there is melt at the core mantle boundary? Well, there are a few lines of evidence to suggest that there might be melt or partial melt at the core mantle boundary and ways that could get there. So one such idea would be, for example, basal magma ocean. So the idea here is that the mantle starts off liquid and solidifies through time. And in the present day, potentially we could be left with melt or pockets of melt or melt residue at the core mantle boundary. Another way to get melt at the core mantle boundary is by present day melting of the mantle. Various people have modeled this. It's been suggested that partial melt could be a possible origin for ultra low velocity zones, for example. And depending on the input parameters to your model, it is possible to melt the lowermost mantle. But one of the problems here is that the melt tends to be iron rich and metallic and dense, and therefore tends to drain from the ULVZs to form an almost global layer at the core mantle boundary, which would appear to be inconsistent with some seismic observations. Geochemistry also gives us arguments for deep geochemical reservoirs, potentially some sort of layer at the core mantle boundary could become entrained into plumes, and those signatures could end up at ocean island basalt. So the overarching question of my research is melt at the core mantle boundary inconsistent with current seismic observations? And how much melt could we have at the core mantle boundary before it becomes seismically visible? So I'm going to be talking to you today about one particular phase quite a lot, which is P2KP diff. It's quite a niche phase, so I'll quickly explain what it is. So P2KP is a P wave which has two mantle legs and 2 outer core legs with an underside core mantle boundary reflection in the middle. Most epicentral distances, there are 2 branches of P2KP. There is the deeper diving BC branch shown here in blue and the shallower diving AB branch shown here in black. As we increase the major arc epicentral distance between our source and our receiver, P2KP AB starts diffracting along the core mantle boundary. And because it has 3 possible core mantle boundary interaction points, there are 3 possible diffraction points shown here as 1, 2, and 3. And it can diffract either at 1, 2, and 3 or a combination of. So the first question we wanted to answer was what seismic phases are sensitive to melts or low velocities immediately above the core mantle boundary, and what phases could we use to detect that? So we did this with forward modeling. So we used Axisem to produce 2-second synthetic seismograms. Axisem is a massive forward modeling software. You input a velocity model. It then builds an earth, propagates seismic waves through it to produce a wave field that we can sample at discrete locations on the earth through time to give us seismograms. So essentially, for an input velocity model, it tells us what the seismograms should look like. So as well as testing Prem as a reference case, we also inserted melt at the core mantle boundary. Now the melt we used was very extreme. We can see velocity profiles on the left here. It's about 33% slow with a sharp discontinuity on top. And this is a very extreme case, but it's an end member case to show us what phases might be sensitive to such a structure. And we can see in these figures here that there are a number of differences. For example, PCP at short distances has greatly increased amplitudes. Also, almost all branches of P2KP have these amplitude anomalies. We can also see that the P2KP diffracted phase, which is this phase here, there's a delay between the red peaks, which are with melt, and the black peaks, which are without melt. Now, there are a number of reasons why amplitudes are difficult to work with, which I won't go into right now, but for our study in particular, the amplitudes depend on what we assume about the layer, particularly about the top of the layer. So for example, if we smooth the layer top, then we lose almost all of those amplitude anomalies. So this is for a gradually decreasing velocity. It's also slightly less extreme. But one thing that we do maintain in all cases is this delay in P2KP diffracted. So that seems to be the most robust measurement that we can make. The differential time of P2KP BC is not affected by putting low velocities immediately above the core mantle boundary, at least not greatly. So if we were to take a differential time between these 2 phases, then that could be indicative of melt or low velocities at the core mantle boundary. So when we do this to our synthetic seismograms, this is what we get. So on the y-axis of these plots, these are differential time residual. So this is the observed or measured differential time minus the differential time in the reference case. So a positive residual implies our phases are further apart than the reference model predicts. Darkening colors just indicate thicker layers. And on the right-hand figure, we plot the mean differential time residual against layer thickness. And we can see that as we increase layer thickness, we also increase our differential time residual. So now that we've found a potential measure to look for these things, we need to then look at some data to learn something about the real world. So first, we need to find events that are suitable. For this study, we need to use quite deep events, and the reason for that is that the depth phases of P2KP BC overlap with the diffracted phase for shallow events. So we can only use depths deeper than 350 kilometers. We also have to use quite large events in order to produce detectable arrivals. Once we've got our events, we then need to find a load of stations within our distance range. To improve signal to noise ratio, we then group our stations into pseudo arrays, and we just do this by interstation distance. Within each stack, we then filter, within each array, we then filter and stack the vertical component envelopes. We then do some quality control to remove traces that have no arrivals of energy or weak arrivals of energy. And then with everything that's left, we measure the differential times, and we do that by cross correlation. So here are some example waveforms. These are at 79 degrees distance, so they're right at the end of our distance range. On the left, we have P2KP BC. the center we have the diffracted phase, and on the right we have the cross correlation function. And we can see we have very, very clear arrivals and a very clear cross correlation function, and we take the offset between these phases to be the peak of the cross correlation function. So when we collate all of this into a global data set, this is what we get. So in this map, we have red stars are our suitable events. We have 315 suitable events. Geographically, they tend to group together just because of where earthquakes happen. Black is our stations. Green are where we have interactions between P2, KP, BC and the core mantle boundary. And blue are our potential diffraction points. Bear in mind, the coverage is slightly complicated because we have 3 diffraction points per measurement, essentially. In total, we have over 12,500 measurements, which is quite a lot. And we have them along the entire distance range. So here are some example waveforms plotted with distance, just so you can sort of see what they look like. This is the BC phase and this is the diffracted phase. So this is our input into our cross correlation. So when we input those into the cross correlation, this is what we get. So on the y-axis here, we have the differential time residual. So again, positive values are the phases are slightly further apart than we predict. Negative values are slightly closer together than we predict. And in this case, we're using Prem as our reference. You can see that in general, we're ever so slightly positive, but we also have a lot of scatter. The scatter has a standard deviation of about 0.7 seconds, which when we think that 1 kilometer of our extreme melt produces a residual of about half a second, that's quite significant. So this is a little summary figure, which looks at different models. So we tried 3 different 1D models, and we also tried our melt models, which are based off Prem. So on the y-axis here, we have the mean differential time residual relative to that model. So Prem, for example, being slightly positive on this left-hand figure, maps to this point here. And error bars are 1 standard deviation. So a well-fitting model would have a mean residual of 0. So for a Prem like Earth, our best fitting model would be about 3 to 5 kilometers of melt at the core mantle boundary. But due to the scatter in the data, it's also possible that Prem within 1 standard deviation is about as well fitting as 8 kilometers of melt. So we can't observe this layer if it exists, but we also definitely can't exclude it. And within the scatter of the observations, there is potential for up to several kilometers of melt or extreme low velocities at the core mantle boundary. It's worth pointing out that in our synthetic testing, this phase pair was the most sensitive phase pair to these structures. And so it seems relatively likely that if this phase pair can't resolve such a structure, then other seismic phases probably can't either. This gets slightly more interesting when we start looking at some statistics. So this is just the means and standard deviations for individual events worth of data. And on the y-axis, we have the number of events that fall within that particular bin. Per event, due to just locations of events and stations, we tend to have particular geometries. So if we look at the standard deviations, for example, the global standard deviation is plotted as this dotted black line, whereas the standard deviations for individual events tend to be much, much lower. This indicates that while we have a lot of scatter in the data set, this is between events and is not an inherent property of the core mantle boundary, and that we have consistency in individual geometries. And the means spread nicely around the global mean. So if we assume for a second that this is some sort of melt or low velocity layer at the core mantle boundary, then in some places it would be thicker and in some places it would be thinner, which is probably what we would expect in a convecting mantle anyway. So we've shown that potentially there could be seismically invisible melt at the core mantle boundary. That would be very, very difficult for seismology to observe. So what would be the implications of this? Well, we've already mentioned in the introduction that geochemistry provides evidence for deep lower mantle reservoirs that are sampled by plumes. That could potentially be something along these lines. Melt at the core mantle boundary could also facilitate core mantle interaction, as we heard in the last talk. This could help explain, for example, core signatures like tungsten isotopes and osmium isotopes that could transfer from the core into this melt before being entrained in mantle plumes. It's worth noting that the composition of melt at the core mantle boundary would depend very heavily on its origin, which is something that we as seismologists can't really say anything about. So in this left-hand figure, these are proposed trace element concentrations for a basal magma ocean. They're shown as black diamonds, and the solid mantle is shown as light squares. You can see that for most trace elements, a basal magma ocean will be relatively enriched. Importantly, in neodymium, saminium, we're also quite depleted in hafnium, which is quite interesting with potential implications for tungsten. We're also enriched in uranium, potassium, and thorium, which are our main radiogenic heating components. So potentially that could have implications for core mantle boundary heat flow if you were to concentrate these elements immediately above the core mantle boundary. Some thermal models of the Earth require a lower mantle radiogenic heating component, and that could potentially be something like this. There would also then be implications for core mantle coupling. As we've already heard from Richards, there is plenty of evidence from mutations and length of day in geomagnetism that the core and mantle are electromagnetically coupled. And that would generally require a conductance of around 10 to the 8 Siemens. If we attribute all of that to our layer, which we think would probably be iron rich, then we have a trade-off between the thickness of the layer and the conductivity. So for a layer between 1 and 10 kilometers thick, we would require an average electrical conductivity of around 10 to the 4 to 10 to the 5 Siemens per meter, which lies somewhere between the electrical conductivities of iron and for normal silicate low mantle rocks. So it would potentially be a realistic value for such a feature. There would also potentially be implications for geodynamics. How would melt at the core mantle boundary interact with ULVZs and with LLVPs? For example, with ULVZs, they could be some sort of feature of this layer, potentially chemical or topographic anomalies within it. So on to my conclusions then. Synthetic modeling has shown that P2KP diff is sensitive to core mantle boundary structure. It's readily observable in data and has been previously underused. We constructed a data set of over 12,500 observations of P2KP diff minus P2KP BC, and that couldn't resolve a melt layer. But within our observations, potentially there could be several kilometers within the scatter. As I mentioned earlier, if this phase pair can't illuminate it, other phases potentially can't either. And if there is seismically invisible melt at the core mantle boundary, that would have implications for previous observations in other disciplines. Cool, and I'm happy to answer any questions.
Thank you, Stuart. So we have a question from Sheila in the question and answer. If the diffraction process wavelength, is the diffraction process wavelength dependent? If so, might that change the shape of the seismic wavelet compared with the straightforward PKKP, so that cross correlation might not always identify the arrival time reliably?
Yes, I guess that is a concern. We do go to quite high frequencies. Yeah, I mean, that's always a danger with cross correlation, right? In that if your waveforms aren't similarly shaped, then you can run into issues. But we do try and limit that with our quality control as well. I hope that answered the question.
Okay. Unless something else appears. So do we have any other questions for Stuart? Okay, if not, I'm going to dive in with one of my finishing comments before, in case everybody leaves. So Sue Bowler, who I think is still here, is the editor of astronomy of A&G, and has asked that we could produce a report of this meeting, not least to make sure that geophysics receives the a profile within the A&G community. And in principle, I probably should write it, but in practice, I'll probably get it wrong. So what I'd like to do is ask the speakers, if they could, to write a paragraph or two summarizing what they presented, and then I will edit it together and produce an article for A&G, if that's possible. If any of the speakers object to that strongly, then feel free to tell me to go away. But I think it would be lovely to expose what we're doing to the broader Royal Astronomical Society community. Thank you very much. So Jenny, after having just given you some work to do before we've even started, I hope you're still going to talk to us. So are you there?
Yes, can you hear me?
Yes, so Jenny is used to me dumping random stuff on her without expecting it. So it's a kind of for old time's sake, isn't it, Jenny?
Yeah, quite. Okay, can everybody see my screen all right?
Yes, I can, certainly.
Right. Okay, well, in that case, yeah, thanks for giving me a chance to talk today. Mainly at request or because I didn't feel like I had time to produce a poster. So thanks to the organizers. So I'm going to talk about some work we published earlier this year, looking at high resolution imaging of the Hawaiian ultra low velocity zone. So this is work that I did with Sana Kotar's group in the University of Cambridge, just before I moved to my new position in Durham, with a little bit of help from Sima Musavi as well, who's based at Australian National University. So apologies for people like Stuart who are part of Sana's group who will have heard this all before. So I'm gonna go through this step by step. Most of you will already know what ultra low velocity zones are because we've heard of them several times in the previous talks so far, but we'll just go over the general characteristics that we know already and specifically focus on the Hawaiian ultra low velocity zone. And then I'll tell you about the data that we've used in this study to try and image that a little bit better, how we went about analyzing that data, and finally what we think these data can tell us about the Hawaiian ultra low velocity zone and maybe ultra low velocity zones more generally. So ultra low velocity zones are an interesting feature of the core-mantle boundary. They're very small, much smaller than most of the things we've been talking about so far, but they're very, very extreme. And we've got wide variations in the reported velocity contrasts in ultra low velocity zones, but there's reports of shear wave velocity reductions of between 5 up to 50%, and compressional wave velocity reductions of maybe up to 25%, and suggestions that they are significantly denser than surrounding material as well. But as I said, they're probably quite small features. We generally tend to think of these things as only being tens of kilometers high and hundreds of kilometers across, which is obviously quite large, but on the scale of the things we can normally see on the core-mantle boundary, these things are pretty small, which makes them very difficult for us to image. There's been suggestions that they might be linked to the base of mantle plumes, and there's been a couple of different studies which have claimed to observe ultra low velocity zones at the base of major mantle plumes, including Hawaii, Iceland, and Samoa. And I know Sana had some work looking at potentially one beneath the Galapagos as well, which I think is still in progress. And there has been a suggestion that they are linked to large low velocity provinces, which we've already heard a lot about this session. So this is a recent compilation study from 2018 that Ewan Gennaro put together, which compiles all of the previous studies of ultra low velocity zones. So you can see here, red colors show where they have been seen before, blue where there's no detections, and yellow where there's some uncertainty. And it's worth pointing out at this point that we really do not have global coverage of where ultra low velocity zones are or aren't. And there has been some recent developments of this with Mike Thorne has had a recent paper out with more global coverage, but it's worth noting that our link between ultra low velocity zones and large low velocity provinces, which are shown here in these pale pink colors, I think it's fair to say is reasonably tenuous. Yes, we have observations of them at the edges of these things and maybe within the center of them, But we also have large areas where we have no observations at all. So maybe this link is a little bit more uncertain than we usually think about in terms of the links that we report. And we don't really know what ultra-low velocity zones are. There's lots of different models that have been put forward, and we've heard some today. The two end members when we think about these things is that they are purely thermal in terms of some kind of partial melt, or they are purely compositional in that they are a solid that's potentially enriched in iron. And of course, these are end members, so we could have a partial melt, which is also compositionally distinct from the rest of the mantle. And just some of the ideas that have been put forward to explain ultra-low velocity zones range from things like there's some connection to subducted materials in relation to partially molten basaltic material or slab-derived metallic melts, interactions between the mantle and the outer core, or that they represent some kind of a primordial remnant of a basal magnet ocean. So there's still a lot of open questions here about what these features physically are. And one of the ways that we might be able to go about thinking about which of these is correct is by looking at geodynamic models. So if we think about a purely thermal explanation for ultra-low velocity zones, geodynamical modeling, such as the example here shown from Lee et al. 2017, suggests that we'd expect them to really be found in the hottest regions of the lower mantle, maybe towards the center of large low velocity provinces, the base of plumes, but we'd expect the shape of them to be reasonably symmetric. Alternatively, if these are solids but compositionally distinct features, we might expect them to look more like the example that's shown in the bottom here, where the material tends to get swept to the edges of large low velocity provinces, and it tends to be more variable and patchy with quite asymmetric shapes to the ultra low velocity zone piles. And the sort of aspect ratio of these things, their height compared to their width, can tell us something about the potential density or viscosity of the material itself. So lots of open questions. What are ultra low velocity zones? How do they form? How do they evolve with time? And what is their potential role in convection in terms of their links to upwelling plumes and subducted material? If we want to be able to answer these questions, what we need is seismic observations, because these are pretty much all we've got to go on in lowermost mantle observational data. And what it would be really great to know about is the detailed shape, the characteristics, so the actual velocity contrasts that we're looking at, but also the global distribution and how variable all of these things are when we have that global distribution. So in this talk, I'm not obviously going to answer all of these potential things that it would be nice to talk about, but focusing on the detailed shape of ultra low velocity zones, and one in particular where we've got excellent data coverage. So there's a couple of different seismic phases that are often used to image ultra low velocity zones. These range from diffracted waves, such as P and S diffracted waves, which graze along large areas of the core mantle boundary, which are very useful but are sensitive to quite a wide area. There's also been a lot of use of SKS phases. So these are phases that travel through the outer core and have potential sensitivity to the core mantle boundary at both the entry and the exit points. And reflected or converted phases. So things that either bounce off the core mantle boundary or are converted from S to P at the core mantle boundary itself. And the one I'm going to be talking about today is these ones. Mainly because these give us quite a small area of sensitivity just around the bounce point of the conversion point. I'm going to be focusing in on the Hawaiian ultra-low velocity zone in particular, which sits here at the edge of the Pacific large low velocity province. And what this pink color here is showing is the large low velocity province based on areas where many tomographic models agree on the presence of slow velocities in the lowermost mantle. So it's another one of these vote maps, which Paola was talking about earlier. If we zoom in on just one of these tomography models in particular, so this is the gypsum model, you can see Hawaii sits here, potentially right at the edge of this large low velocity province feature. Now, there has been many studies that have looked at the Hawaiian ultra low velocity zone before. These range from things that use PCP waves, reflected P waves, reflected S waves. That was a whole set in the mid 2000s. There was quite a lot. There was some more recent ones looking at differential times and there has been a few using diffracted waves as well. And what you can see, if you have a look at where these different studies are sensitive to, is that we have a huge variation in reported properties of the Hawaiian ultra-low velocity zone. The height, it varies from each of these different studies, varies from maybe as small as 5 kilometers in height, maybe as up to as much as 80 kilometers. And the velocity reduction might be as small as 3%, which is more on the scale of a large low velocity province, or maybe up to 30%. And even we can see that there's different locations where this thing is supposed to sit. Is it to the west of Hawaii? Is it to the east? And exactly where does it sit in this area? So it's not clear that, that these studies are consistent with each other or not. The question that would be really interesting to know is if we can get a large-scale regional analysis that covers this whole area, are we going to see that this is in fact a larger scale feature which has very variable properties? And so these models are just seeing different bits of a variable feature, or are some of them more or less correct in their proposed descriptions of the ultra-low velocity zone? And so that's what we wanted to go in and do, to kind of have a look at a large scale consistent analysis across the whole area. To do this, as I said, we're going to use reflected waves. So specifically, we're using SCS phases that bounce off the core-mantle boundary from deep earthquakes, and we need to use them from distance ranges of about 70 to 90 degrees. Now, Hawaii is really well placed for this kind of study, which is why we chose it. We have lots of nice deep earthquakes happening over here in Fiji and Tonga and Papua New Guinea. And we have the amazing large-scale deployments of the US array and then the Alaskan transportable array, which means that you do get like quite a large coverage around this area. And so this is, the black points here show you the bounce points of SCS waves for these earthquakes and these stations. So for every single one of these observations, we're going to look at data within the 30 seconds to 2.5 second frequency band. And we're specifically looking at transverse data. This is because we don't have to worry about converted phases at the core-mantle boundary if we look at horizontally polarized S waves. So we looked at this data in a couple of different ways. The first one is to measure differential SCS and S travel times. So we can have our S wave and we can have our SCS wave that bounces off the core-mantle boundary. Now these two phases have very similar paths in the upper mantle on both the source side and the receiver side. So the idea is that when you look at the differential times between the two phases, you're really sensitive just to the lowermost mantle where there is a difference between the ray paths. So the way that we make these measurements is we have a predicted arrival time between S and SCS for a known velocity model, in this case PREM. And then we compare that predicted time to an observed time between the SCS and the S wave. And this is the measurement we're interested in, the differential of the differentials, as it were. So the differential time between the observed difference and the predicted difference. Now, this is obviously very sensitive to your choice of velocity model that you're comparing to. And so we started off looking at PREM, which is a nice, easy 1D reference model. We also chose to compare to a bunch of different 3D tomographic models to see how consistent our results were. So you can be quite agnostic if you're not a tomographer in which of these models is your preferred one. This is the results from that analysis. So we've got about 8,500 point measurements. And you can see here the differential times that we're measuring. So the red colors here suggest that there is a slower than predicted velocity structure in the lowermost mantle compared to our reference model. And blue colors show that it's faster than predicted. What you can see is there's a lot of scatter here, but across much of the data set, we've got really strong delays of maybe up to 10 seconds. And this is relative to PREM. We can do some geographic binning to tidy up the mess of the scatter so we can see things a little bit better. And this is the kind of structure that seems to show us. So you can see we have very strong delays both to the west of Hawaii, but also to the east of Hawaii as well, which falls off as we move further away. As I said, this is relative to PREM, which is a 1D structure and doesn't take into account what we already know of the slow velocities on a larger scale already from tomographic models. So if we look at the same kind of data analysis, but compared to different tomographic models, you can see that they're all shown here. The first thing you notice is as soon as you apply these 3D models, there's a big reduction in the amounts of the differential times, but there is still strong delays of up to 6 seconds, even when you account for the already known long wavelength structural variation. And we can do things as Paolo was showing us before by looking at vote maps and seeing how consistent our observations are depending on across our different tomography models. And you can see here areas that really show very consistently between whichever model we choose, strong delay times. And this is the average of all the 3D corrected models. So what this tells us is that we have strong delays independent of our correcting model choice. So we've got widespread slow material in the lowermost mantle around Hawaii across a really large area, actually, much larger than the typical areas that we think of for ultra-low velocity zones, which is only a couple of 100 kilometers across. And this is velocities that is not accounted for in our long wavelength tomography models that we normally look at. So the second way that we looked at this data is to look at something called pre and post cursors. So these are small phases that we see around our SCS waves. So when you have an SCS wave and it bounces off the core-mantle boundary, if you have an ultra-low velocity zone, which has a sharp top to it, you can also get precursors, which bounce off the top of that layer, and so arrive a little bit earlier with a negative polarity. And you can get post-cursors that bounce around within the layer before arriving a little bit later. So you have this nice negative and positive on either side of your main phase. So we can look for structures like this, which will tell us something about ultra-low velocity zones. And what's really nice is that while our SCS minus S times are sensitive to lower mantle structure within the bottom hundreds of kilometers, these are really only sensitive to the velocity structure within whatever basal layer is setting up the arrivals. And the way that we can look at these carefully and sort of make them a little easier to see is using something called flip reverse stacking, which basically just says these precursors and postcursors should arrive at similar times on opposite side of our main phase. The only difference should be the polarity. And so we take the waveform preceding our SCS phase, we reverse it in time, flip it in polarity, and add it together. And that really emphasizes any pre or post cursors that are present. And it also cancels out the central peak, so we can see things a little bit more clearly. And so what we did is we took all of our data and we propagated it into a large 3D grid. And it's stacked not just at the bounce point, but over the Fresnel zones, the area of sensitivity of the wave. And that gives us this kind of data coverage over the whole region. We then go through this and look for peaks, which are the first arrival above the core-mantle boundary, because that's what's going to be defining for us our basal layer. And we have some quality controls that say we must be able to see both a precursor and a postcursor, and it must be above 2 standard error of the mean. And when we do that, this is the kind of results we see. So the gray areas here are where there is no data picked. Then the colored areas are where there is data picked. And the color bar here just shows you the relative arrival time of those pre and post cursors. So darker red colors show you a greater arrival times, which suggest either a thicker or a slower layer. We can also think about this in terms of the changing amplitude of the arrivals that we can image as well. And so what I'm going to show you now is some cross sections through this 3D grid, so you can see what these arrivals actually look like and how they vary across the area. So we'll start off looking at this one where we go through this large observation to the west of Hawaii, which seems to be seen very strongly. So this is what this cross section looks like as we move from southwest to northeast across the profile. And you can see above the core-mantle boundary, our first arrival is a really nice, strong arrival showing these pre and post cursors. Further to the east, we still see an arrival just above the core-mantle boundary, the first one, because that's what we're interested in, the basal layer here, but it's much weaker and it seems to show some variation in the arrival time. We look at some cross sections in the other orientation, again, we can see this kind of variation as we go from the east, where we have a potentially variable and slower or less slow or thinner layer, moving into this large layer as we come up to the west. And you can see as we move into this gray region, we have less data and things start to get very messy and it's hard to know what's going on at this point. And the same can be seen a little bit further down. There's suggestions of faint arrivals here coming into this large positive thing to the west of Hawaii before we get into our low data coverage region. The other interesting thing to note here is down here to the south of Hawaii itself, we have this really interesting region of really large changing polarity amplitudes, which I will come back to at a later point. So we had our two methods of analyzing this. We looked at our SCS minus S differential times, which is sensitive to the bottommost hundreds of kilometers of the mantle, which told us there is widespread slow material over quite a wide region that is not currently accounted for in tomography models. And on a smaller scale, the pre and post cursors, which can really tell us about material that's constrained to the basalmost layer and it has to have a sharp top, suggests that there is a kind of basal layer with a sharp top across much of this area across Hawaii. But it's clearly quite variable because the arrival times are very different and so are the amplitudes. So if it's there, it has very variable properties. So the next step is understanding what these arrival times actually mean. And now this is where we encounter a problem which happens throughout ultra-low velocity zone imaging, which isn't much talked about, in that we have a massive trade-off problem. So when we have our pre and post cursors, we can cause increasing delay times around the main phase by having an ultra-low velocity zone with different velocity contrasts. So as we increase the velocity contrast, the arrival time moves out. Equally, we can produce exactly the same result by having an ultra-low velocity zone layer, which is of varying height, which can cause increased move out. And so we have this perfect trade-off between ultra-low velocity zone thickness and velocity contrast. And so I would say this is a take-home message. When you see studies of ultra-low velocity zones from seismology and they report a specific best fit height and velocity contrast, remember all methods have these kind of trade-offs, which are not often acknowledged. Now, interestingly, this is the trade-off curve that you see for the pre and post cursor method that I talked about. This is the trade-off curve that you see for the SCS minus S differential time method. These both suffer the same kind of trade-offs, but interestingly, they're slightly different trade-offs from each other. So what we decided to do at this point was to take a method which is commonly used for crustal imaging, which many people may have heard of before, that is HK stacking, and convert it for use at the core-mantle boundary. So HK stacking is a way of looking at converted phases and measuring the thickness of the Earth's crust in a very, very simple model where you simply measure H, the crustal thickness, and K, the VP-VS ratio of this structure. And the idea is as you go through your 2D model space, you predict the arrival time of different phases and you pick them out. And if you pick your correct model, you will pick all of the large amplitudes and they will stack to a large amplitude here in your HK stack. And that'll allow you to pick your best fitting crustal thickness and VP-VS ratio. So we decided to do exactly the same thing on the core-mantle boundary, except in this case, what we're measuring is H, in this case, the thickness of our ultra-low velocity zone, and V, which is our ultra-low velocity zone velocity contrast. Now, most of the time, this would just tell us our trade-off. And that's already somewhat useful because it can tell us minimum and maximum potential heights within a realistic range of velocities. But because we've also got this slightly different trade-off from our SCS minus S differential times, if we combine these two things, we can actually downweight areas of that trade-off curve which are less likely to be realistic, and potentially in this perfect synthetic data, find your best fitting input model. So this is what we did across this data set. It's been carried out in a couple of these different regions here. This is the data that's going in. These are our pre and post cursors that we see in each of these regions. And these are the HV stacks that it gets you out in the end. Now, what you can see is that, unfortunately, it doesn't really seem to pick out very well a best fit model, but we do have the trade-off curves defined very nicely. And as I said, this is already useful because it gives us a maximum potential height of our ultra-low velocity zone within realistic velocity contrasts. So unless we go ridiculously high in our velocity contrasts, this structure is not going to be above about 30 kilometers in height. However, if you look at the range of these trade-off curves, you'll see that there is a possible consistent height of about 10 kilometers that could explain all of our observations. However, if we want our structure to be the same height everywhere, this would require the times that we see to be explained solely by velocity variations. And that suggests that the velocities would have to be changing in this material from -5 to -50% over this area, which seems unlikely, especially given that velocity changes would also probably be linked to density changes. And so the idea of having a layer of consistent thickness is probably unlikely. We can also try and put some more constraints on here. So I know we had a range of very different models initially suggested from previous studies, but most of the more recent ones fall within a range of 10 to 30% velocity reduction. So if we apply this constraint to our trade-off curves, we can link this, we can reduce these a little bit more, and we start to see suggestions that there really is height variation within this layer. And again, we can look at where the maximum amplitudes are in these trade-off curves. And if we just look at the strongest amplitudes within 90%, we can see that while some of them, that doesn't really tell us much, on others, it really says that the structures have to be on the higher end of these trade-off curves. And again, we've got the suggestion of that we really are having variations in the height of this layer across the area. And again, we can make this assumption if our layer is a consistent velocity everywhere of approximately 20%, which is about the middle of previous estimates, we can convert these arrival times into potential height changes in the structure. And that suggests we'd require changes in topography between 5 to 25 kilometers across the area, which seems much more realistic and in line with previous observations of ultra-low velocity zones. And so while it's not entirely possible to say, we are very much of the opinion that variable topography explains these observations much better than huge variations in velocity contrast. Okay, so what does this data actually tell us about the Hawaiian ultra-low velocity zone? So there's a couple of key features that jump out. We've obviously got this large structure to the west of Hawaii that we see in both of our methods. It's thousands of kilometers wide. It's the tallest part, probably 15 to 25 kilometers thick, and has velocity reductions of up to 20% or lower. We've also got this sort of elongated feature to the east of Hawaii, which can be seen here. Again, heights of up to 25 kilometers, but very variable, and interestingly getting thinner as we move inwards towards the large low velocity province. And we had this interesting region down here to the southwest, which is where we had these changing polarity arrivals, which may be suggestive of layered structure of positive and negative velocity contrasts. The first thing to say is that this is really nice because all of these areas fit really well with previous studies. So the Western mega ultra-low velocity zone, which I've called it this, is because it's been noted before in diffracted wave studies, and it sits right in the same kind of place. And then the previous studies of reflected and converted phases really seem to align with observations of this structure in the east, and the variable heights of those previous observations linked to the height changes that we suppose this layer is having. And then that complex region down here has been modeled in great detail previously and suggested to have things like a post-Bridgmanite lens, which might explain those alternating layers that we think we see. So nicely, our observations are consistent with the previous studies, and it suggests that these previous studies have just been imaging different parts of a highly variable feature rather than being inconsistent with each other. The next thing it's interesting to think about is how this small scale seismic observation relates to the large long wavelength structures that we can see in tomography models. So here I've just put on the contours of the gypsum tomography model here, so you can see the outline of the large low velocity province and also these high velocity regions. And what's interesting to note here is that our piles of material where we think they are highest seem to be sandwiched between the large low velocity province on one side and these faster observations in the tomography on the other side. So maybe what we're seeing here is material being piled up between remnants of subducted slabs and these fast materials against the edge of large low velocity provinces. And that's why we've got the largest heights in our ultra low velocity zone material here. The other thing to note is that recent tomography studies, such as this one from Husseini et al. In 2020, seem to suggest that the Hawaiian mantle plume may be offset at depth from the surface expression slightly to the west, which would mean that this area here, our western mega ultra low velocity zone, may well be representing the base of the Hawaiian mantle plume at depth. So this is the kind of picture that this leaves us with in terms of an interpretation. We have an ultra low velocity zone which is much, much bigger than we are used to thinking about. This is not an ultra low velocity zone which is 100 kilometers across, as most things are reported to be, but is on the order of thousands of kilometers across and is very variable in its height, we think, from anywhere between as little as 5 kilometers, which is the limit of our resolution, up to about 25 to 30 kilometers height at its maximum potential range. But we know that the velocity reductions are unlikely to be greater than about 20%. Also, it's got this asymmetric shape, particularly here in this eastern pile as we move into the large low velocity province, which is much more consistent with geodynamic models which suggest a distinct dense but solid material, rather than those purely thermal models which would suggest a more asymmetric shape is what we would be expecting. And the fact that we seem to see suggestions of this material being piled up between fast and slow regions in tomography models, which may represent slabs and large low velocity provinces, maybe is indicating to us that what we're seeing is some kind of passive material that's being shaped by other mantle processes. So this is the kind of conclusion of this study. I'd also like to take a moment here just to put a tantalizing question, because one thing I didn't mention about these observations that really stood out, which we don't have an explanation for, is that the SCS amplitudes of these phases are really big. They're much bigger than we were expecting. In fact, in some places, they're bigger than the direct S wave. Now, that's very unusual because this is a wave that is traveling further and should be losing energy at its reflecting point. So this is the range of the amplitudes that we see, and this gray area shows the predicted amplitudes. So the amplitudes of these SCS arrivals across this region are really big. And if we look at how the amplitudes vary, what you can see is the largest amplitudes seem to correlate with the areas of the greatest delay time in our other measurements. So there seems to be some kind of link with this ultra low velocity zone material and these increased amplitudes. And this is an open question which I don't have an answer for, with a potential tantalizing explanation that maybe what we're seeing here is some kind of small scale core mantle boundary topography causing focusing of the reflected phases. But I thought I'd leave this open because I'd love to hear anyone's ideas about this. Yeah, so thanks very much, and I'd be very happy to take any questions.
Thank you very much, Jenny. We don't have anything in the Q&A or the chat at the moment, but does anyone have a question they would like to raise? If not, I'll have one, but relating to that last kind of very interesting point about the idea of focusing the stuff and having much larger magnitudes. So if you, this is maybe a silly question caused by an ignorance of seismology, but if you focus it and put all the energy in one strong thing, presumably there's less energy somewhere else?
Yeah, I don't know. It's kind of something I really want to explore in terms of the modeling. The idea is if you have your focusing like this, you are having multiple rays like a lens type shape coming in at one point. I don't know if that necessarily means that you have less focusing elsewhere, because that would depend on having a convex, the opposite kind of orientation somewhere else. So if you have a depression somewhere, it doesn't necessarily mean you have the opposite somewhere else, I suppose.
Right.
But I don't know. I haven't done the modeling yet, so.
Do you think you can?
Interesting to see. Theoretically, yes. I mean, I think AXISM 3D allows for topographic variability to be input in. So, yeah, when I find the time, it would be great to find out.
Yes, well, if you're anything like me when you retire, I know that feeling. So we had a question which now hopefully is made.
No.
No, okay, well, we had a question in the Q&R from Sheila. Did I miss it, or have you considered anisotropy?
You didn't miss it. We haven't considered anisotropy. It's something on the to-do list. It would be really interesting to see if there is any shear wave splitting in these arrivals. That would be a really interesting thing to do. The problem comes in that when you start looking at SH versus SV, for your SV waves, there's a potential that they can get converted at every boundary that you have. So the core mantle boundary, but also potentially the top of your ultra low velocity zone layer. So your arrivals might get very complicated. Whereas so far we've just concentrated on the SH components because we don't have to have those, we don't worry so much about those kind of conversions. But it's on the to-do list. It would be very interesting to see if there's variations in anisotropy across the region as well.
Right, so there was some indication that Ryder might have a question. So let's see if we can let him talk.
Okay, can you hear me?
Yes.
Okay, no, it was a very nice talk, Jennifer. It looks like this irregular ULV body is kind of almost following the outline of the LSVP, at least from in some of the models that you showed imposed on it. Is that your impression then?
Yeah, I mean, it's hard to tell. I think to the east, we do seem to see that suggestion of as we move into the LLSVP, definitely this layer is getting thinner and thinner. The problem is we still have limited data coverage. We've got huge regional coverage compared to most models, but at some point we don't know what's outside of that region. If you move far enough away in the west, it's not present anymore for sure. But if you were to move further away to the north, hopefully it would disappear, but we're not sure. And again, if you move further to the south into the LSVP, maybe it would disappear. It's definitely getting thinner, but we don't have the data coverage to confirm that for certain. We only have this suggestion that it's getting less.
Yes, thanks very much for the answer.
Okay. So if we don't have any further questions.
Could I ask one, Richard?
You? Yeah, maybe. If you've been quite good, yeah.
It's another dumb question though. So I'm
sure it's not.
You've gone muted, Chris.
Oh, I haven't.
That's
muted.
better.
Do you have any ideas for what causes the variation in topography on top of the ULVZ? Presumably that tells you something about what it's composed.
Yeah, I mean, so potentially. So if it is a variation in topography, and I think hopefully I've stressed here, that's my preferred interpretation, but you could just say it's got massively varying velocity variations instead. I think, well, I mean, the thing that occurs to me is that it's a mechanical effect, because you see this change of the highest regions between the large low velocity provinces to the south and these fast anomalies to the north, which suggests it's some kind of material that's getting piled up between slabs on one side and large low velocity provinces on the other, which I think is something that they've seen in some of the thermodynamic models of how this material would get shaped potentially. But yeah, who knows? What's quite nice is that the asymmetrical shape where it's it's got this high topography, and then it goes thinner and thinner as you move into the large low velocity province, especially in the eastern area. That's the kind of asymmetrical shape that they're seeing in these thermodynamic models of a solid URVZ material, which is very interesting. But the fact that you have those fast areas as well, I don't know, maybe it's some kind of passively being pushed around by the other stuff on the core-mantle boundary.
Great, thank you.
Okay, so Kathy had a question about the recording, which I think has been answered in the stuff. It will take some time to process, since the organizers and me will have to do the editing. Should be uploaded to a RAS YouTube channel, so we should be able to get a chance to see these talks again, which, as I say, you've unwisely given me an extra 5 minutes to talk, but I won't use it too much. So I would like to say thank you very, very much, first of all, to all the speakers who gave really great talks, but also very much in the SEDI spirit. There was lots of interdisciplinary stuff, lots of discussions that weren't just aimed at one area of the subject. So it was really nice in that respect. A particular thank you to my co-organizers, Richard for actually making things run, and Chris for saving me from myself over the past week, which meant we actually had a meeting. So thank you very, very much to both of them. Big thank you actually to all the participants. So it's been a really lovely meeting with a really wide audience. We had that little chats around the gather town. I had enjoyed, that was my first experience of it. I enjoyed having little chats with people as I walked around. But that really made it, I think it's been a really kind of vibrant meeting because of the people who've been here, which bring me to a request to the community, actually. So this is, as I said, this is the 5th UKSEDI. As you know, this was, as some of you will know, this was my baby back in 2011. So I've done a few of the organizers on 3 of them. People have filled in. So Paula did the last one, and Leeds Crowd did the second one. It would be really lovely to keep it going. And the RAS provide this facility. I mean, either this kind of facility or the physical facility of Burlington House. And they also, if you're in a normal meeting, you get a paid for American speaker and European speaker in very crude sense. So you can bring across people you want to work with, kind of if you organize the right meeting. And we are undersubscribed in terms of solid earth geophysics meetings that we provide. We have considerable, there is a very much an open door to providing this kind of meeting or any other meeting that you find about solid earth geophysics. So please bear that in mind. But also, if we could have some people to step up to organize the next ones, because I may not be in such a good position to do it in subsequent years. And it would be lovely to see it continue, because I think it's been a very good meeting, not only this time, but in the previous meetings. So thank you very much for considering that. Thank you very much in advance to the poor speakers who I've just got to write a paragraph for me. I look forward to receiving it. And thank you very much for everyone for coming.